Ajib sir, good morning sir. Welcome sir. Sir, we are going to start very soon. Just waiting 1 or 2 minutes. We will be start.
Good morning, everyone. With the blessings of His Holiness Jagat Guru Shri Shivratri Deshkendra Mahaswamiji, I, Dr. Anchal Yadav, Assistant Professor, JSS University, take the privilege to welcome respected Honorable Vice
मैम आपकी वॉइस नहीं आ रही।
Sorry, sir, sorry. Good morning, everyone. With the blessings of His Holiness Jagat Guru Shri Shivratri Deshkendra Mahaswamiji, I, Dr. Anchal Yadav, Assistant Professor, EC Department of JSS University, take the privilege to welcome respected Honorable Vice Chancellor Sir, Dr. H.R. Mahadev Swami, respected Principal Sir, Dr. B. Manoj Kumar, respected Registrar Madam, respected CAO Sir and AO Sir, esteemed Summit Chairperson Dr. Jagdish R.S. Sir, and respected Chief Guest Dr. Rajiv Ranjan Sir. Our respected convener Dr. Arun Kumar and coordinator Dr. Shankar Sir. I also welcome all the distinguished speakers, esteemed faculty members, dear participants joining us through Zoom and YouTube Live. Welcome you all. On behalf of the Department of Electronics and Communication Engineering, JSS University, Noida, I extend a very warm welcome to all of you to this one-day online summit on Silicon India 2030, VLSI and Chip Design Summit from Design to Fabrication. We are delighted that experts and participants from across the country have joined us virtually. Let us begin this auspicious event by invoking the blessings of Almighty with the lamp lighting ceremony and Saraswati Vandana, symbolizing the removal of darkness and pursuit of knowledge.
No, sound is not coming.
Achal, white is not there.
कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना शङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीम् अभयदां जाड्यान्धकारापहा हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्
I now invite Dr. Arun Kumar Ji, Head of Department of Electronics and Communication Engineering, JSS University, and convener of the summit to welcome the gathering. Over to you, sir.
Thank you, madam. Good morning to one and all. At the outset, with the divine blessing of His Holiness Mahaswami Ji, I, Dr. Arun Kumar Ji, Professor and Head, Department of Electronics and Communication Engineering, consider it a great privilege and honor to extend a warm welcome to all the distinguished dignitaries, speakers, faculty members, researchers, students, and participants gathered for today's one-day online summit on Silicon India 2030 VLSI and Chip Design Summit from Design to Fabrication. It is my proud privilege to extend a heartfelt welcome to our Honorable Vice Chancellor, Sir Dr. H.R. Madhav Swami, Sir, our Dean Academics, Dr. Manoj Kumar B, today's distinguished resource person, Dr. Raju Kumar Ranjan, Professor, Indian Institute of Technology, Dhanbad, Registrar Ma'am, Finance Officer, Controller of Examiner, the Submit Chair, Dr. R.S. Jagdish, all the Deans, HODs, faculty members, and esteemed participants who have joined us from across India and abroad. Today, India stands at a defining moment in its journey towards becoming a global semiconductor hub. The Government of India, along with the Government of Uttar Pradesh and several other states, is placing significant emphasis on strengthening the electronics manufacturing system ecosystem, particularly in the area of semiconductor, VLSI, and chip design. Thorough visionary initiative under the Atmanirbhar Bharat mission and the India Semiconductor Mission, substantial investments are made to establish a robust semiconductor ecosystem with a goal of generating more than 1 lakh employment opportunities by 2030. This summit has been organized with the objective of bringing together eminent academicians, industry experts, researchers, and students to deliberate on the latest advancement in VLSI design, semiconductor technologies, electronic design automation, tool, chip fabrication, and emerging opportunities in India, rapidly growing semiconductor sector. I sincerely encourage all the participants to make the best use of this one-day summit by actively engaging in the technical sessions, interacting with the experts, and gaining valuable insights into one of the most promising and transformative technologies shaping the future. I once again extend my heartfelt welcome to each one of you and wish you a successful summit. Thank you, and I wish you all a wonderful day ahead. Thank you. Over to you, madam.
Thank you, sir, for extending such a warm welcome and for emphasizing the importance of semiconductor and VLSI technologies. Now, It is my privilege to invite coordinator of today's summit, that is Dr. Chand Shankar, who is Associate Professor in Department of Electronics and Communication Engineering, JSS University, Noida. He will give us an overview of the summit. Over to you, sir.
Good morning. With the divine blessing of His Holiness Jagadguru Sri Shivaratri Sir, Desikan Mahaswami Sir, respected Honorable Vice Chancellor, Dr. H.R. Mahadev Swami Sir, respected Dr. B. Manoj Kumar Sir, Professor and Dean Academics, respective Registrar, Madam Dr. D.G. Mamta, Summit Chairperson, Professor R.S. Jagdish Sir, Honorable Chief Guest, Professor Rajiv Ranjan Sir, Finance Officer Sir, esteemed speaker from academia, industry, faculty members, researcher, industry expert, students, and participants from India and abroad. A very warm good morning to everyone. I'm Dr. Chandrasekhar. It is my privilege and honor as the event coordinator to welcome you all to the one-day summit on Silicon India 2030 VLSI and Chip Design Summit from Design to Fabrication, organized by the Department of Electronics and Communication Engineering, GSS University, Noida. Today's summit has been envisioned as a platform where academia, industry, researcher, startup, and aspiring engineers come together to discuss the rapidly evolving semiconductor ecosystem and India's journey toward becoming a global semiconductor powerhouse. The Government of India's semiconductor mission and vision of Silicon India 2030 have created unprecedented opportunity for innovation, manufacturing, research, and skilled manpower development. As educators and technologists, it is our responsibility to prepare next generation to engineers to contribute meaningfully to this national mission. This summit has been carefully designed to provide valuable insight into the latest development in VLSI design, semiconductor fabrication, CMOS technology, electronic design, automation, tools, AI-enabled hardware system, embedded technologies, chip architecture, and emerging trends in nanoelectronics. Though the expert talk and panel discussion participants will gain practical knowledge of the latest technological advancement and future career opportunity in the semiconductor sector. We are privileged to have with us outstanding panel of distinguished experts from premier institutes and industry, including Professor Rajiv Ranjan Sir, Professor, Associate Professor at IIT Dhanbad, Dr. Ravindra Jha Sir from IIT Guwahati, Dr. Rajendra Pratap, he is Vice President and General Manager in Valley Semi, Noida, Dr. Swan Sehra, he is Assistant Professor at University of Delhi, Mr. Vijay Kumar, ND, is Director in Proxy Lera, Bangalore. This is a semiconductor company. Mr. Chandan Jha, he is a founder of Semi Semiconductors, Taiwan. Their vast academic and industrial experience will certainly increase today's deliberations and inspire all of us. Throughout the day, participants will have opportunity to engage with expert, exchange idea, understand current industry requirement, explore research collaboration, and discover exciting career pathway in the semiconductor and VLSI domain. We sincerely hope that every participant leaves this summit with new knowledge, fresh perspective, and meaningful professional connections. I extend my heartfelt gratitude to our Vice Chancellor, Sir, Honorable Principal, Sir, University Administration, Organizing Committee, faculty members, students, volunteer, technical team, and every individual who dedicated effort have made this summit possible. I also thank to all distinguished speakers for accepting our invitation and sharing their valuable time and expertise with us. To all these participants, I encourage you to actively engage in every session, ask questions, interact with the speakers, and make the most of this unique learning opportunity. Once again, I warmly welcome each one of you to Silicon India 2030 VLSI and Chip Design Summit from Design to Fabrication. Thank you all for your gracious presence. Thank you. Over to you, Madam.
Thank you, sir, for giving us a comprehensive overview of today's summit. It is my privilege to invite our esteemed summit chairperson, Dr. Jagdish R.S. Sir, to address the gathering and share the vision, objectives, and significance of this summit. Over to you, sir.
Good morning to everyone. With the divine blessings of His Holiness Mahaswamiji, I extend my warm greetings to our Honorable Vice Chancellor, Dr. H.R. Swami, sir, Dean Academic, Dr. B. Manoj Kumar, sir, Registrar, Controller of Examination, Finance Officer, Deans, HODs, distinguished keynote speakers, industry experts, faculty members, research scholars, my dear students, and all participants. It is my privilege to welcome you to Silicon India 2030 VLSI and Chip Design Summit from design to fabrication. As India emerges as a global semiconductor hub, this summit highlights the importance of innovation in chip design, fabrication, packaging, and advanced semiconductor technologies. The semiconductor industry is the foundation of AI, 5G, 6G, IoT, smart manufacturing, healthcare, and next generation computing. I encourage everyone to make the most of today's technical sessions by interacting with our eminent experts, exchanging ideas, and exploring new opportunities for research, innovation, and industry collaboration. I sincerely thank our Honorable Vice Chancellor for his visionary leadership and unwavering support. My heartfelt appreciation goes to the head of the Department of Electronics and Communication Engineering Department and the organizing committee for their excellent planning. I also express my gratitude to our management, distinguished speakers, and all participants for making this summit meaningful. With these words, I wish the summit a grand success and hope it inspires innovative ideas that contribute to India's semiconductor mission and the vision of Vikasit Bharat 2047. Thank you, and I wish you all a fruitful and enriching summit. Thank you.
Thank you, sir. It is now my privilege to invite our respected Vice Chancellor, Sir, Dr. H.R. Mahadev Swami, sir, to deliver the address and to address the gathering. Thank you, sir. Over to you, sir.
So thank you. So very good morning to everyone, distinguished speakers, my esteemed colleagues, industry leaders, faculty members, students and researchers, and ladies and gentlemen. A very warm welcome to you from JSS University, Noida. It gives me immense pleasure to welcome each one of you for this one-day summit, Silicon India 2030, VLSI in Chip Design Summit, from design to fabrication. So when I just thinking what can be done by the EC department and looking at the trend in the industry, requirement of the industry, there are 2-3 things in the electronics and communication. One is the electronics part, other is the communication part. So in communication, so what is the requirement? Requirement is simple. So we have to communicate each other. We are communicating. So how is communicated? We require the communication channel. So that is where the Tarar's communication was taken as one of the topic. Second is to do that particular task, to communicate or processing, whatever, you require the electronics. Then we decided, let's go with the VLSI and chip design. So this is the trend which is in the current trend. Maybe next 5, 10, 20 years, it is going to rule. The VLSI and the other side is the communication. So we are that way we are preparing ourselves, the university is preparing ourselves and also the students. Maybe let us begin with one dialogue. It's a simple dialogue. How many of us, before leaving home this morning, used a device that did not contain semiconductor chip? Anyone? Perhaps no one, right? So the mobile phone is in our hand, laptop is in our bag, or we use, car we travel in, medical equipment what we use, or satellites orbiting the earth, AI system, suppose if you're using AI system, ChatGPT, Gemini, transforming the industries, your household appliances. You may have started with the gas stove or the electric stove or the washing machine. So even that is a contains the chip. Household appliances, all are powered by silicon chips. There's no device, there's no equipment There's no place where there's no silicon chip. Even your watch, anything you take. So you have a electronic. So even in the body, there's a body also we may having a electronic chip. That is the silicon chips. So today, semiconductors, that means semiconductors are no longer just an electronic component. So they are become the foundation of economic growth, technological leadership, and national security and digital sovereignty. So where we are depending on more on the electronic devices or the chips from the various countries like Taiwan or some other country. So today, maybe last few years, which industry experienced, it was there's a shortage of chip manufacturing. That's where they're looking at the India. So today, we are the last 2 years or 3 years, the major industries are set up in the India manufacturing the semiconductor chip. One is in the Dulera, Gujarat, which is a Tata set up, which is already the manufacturing the chip. Probably by every week they're manufacturing about 10,000 something, which I don't remember now. So 10,000 because I had a meeting, met with all the people in the Dulera. So Dulera plant is one area. So next to that is what quantum is coming up, quantum computing. So that is quantum chips design. So that is a nation that designs and manufacture advanced chips will shape the future of the world. So that's how Taiwan was ruled earlier. So those who manufacture the chip, they rule the world. So India clearly recognized this opportunity for last couple of years. So the semiconductor mission, supported by visionary national policies and unprecedented investments, is laying foundation for a vibrant semiconductor ecosystem. New fabrication facilities, OSAT units, design centers, and semiconductor startups are emerging across the country. However, one important reality remains. What is that? So factories can be built in a few years. For example, Tata, they just operationalized in the factory, whole factory, in 2 years' time. When the land is allotted, then the complete 2 years is operational. The manufacturing the plant, chips. Machine can be imported. Whatever the machinery required, you can import. But capital can be mobilized. Any money required, investment required, they can mobilize it. But highly skilled semiconductor engineers cannot be created overnight. The talent, building a talent, it takes time. To develop the world-class talent requires universities, committed faculty, research ecosystems, and continuous collaboration with the industry. This is required. This is where a lot of things are happening across India in the last few years. That is precisely where institutions like ours, JSS University in Noida, have an important responsibility. So at JSS University, we believe that engineering education must move beyond classrooms. Our students should not merely study semiconductor devices. They should design them, simulate them, verify them, optimize them, and eventually contribute to building them also. So this is exactly what is required. We also organize the internal summer internship program on this topic for 5 weeks in association with industries where the students are gained the practical knowledge. This summit reflects this vision. So today's sessions, as elaborated by the convener, cover complete semiconductor value chain from CMOS technology, VLSI design, electronic design automation, EDA, fabrication process, AI hardware, embedded system, and emerging nanotechnologies and India's semiconductor mission. So more importantly, our participants will interact directly with the experts who are shaping the future of the industry. That exposure is often more valuable than many hours of spent reading the textbooks. So dear students who are participating, if you are here, I would especially like to speak to you. You belong to a remarkable generation. Our faculty who are guiding them, they belong to the remarkable generation. Earlier generation have built a software. Your generation has the opportunity to build the hardware that power the AI, quantum computing, 6G communication, autonomous vehicles, medical electronics and aerospace system, and future smart infrastructure. So the demand for semiconductor professionals is growing globally. India is expected to require tens of thousands of highly skilled VLSI engineers over the coming decade. So this is not merely a career opportunity, it is an opportunity to contribute to a national development. So therefore, I encourage all the students to cultivate not only technical competence, but also curiosity, creativity, multidisciplinary thinking, and the confidence to innovate. Remember, great chips are not designed only with the software tools. They are designed by a sharp minds that ask better questions. So, to our faculty members and researchers, this summit should become the beginning of deeper collaborations. Let us build stronger partnership with industry. Let us undertake impactful research. Let us develop indigenous solutions. Let us patent, publish high quality research papers, mentor startups, and contribute meaningfully to India's semiconductor ecosystem. So, universities must be creators of technology, not merely consumers of the technology. Before I conclude, I would like to congratulate the Department of Electronics and Communication for organizing this timely summit. My sincere appreciation also goes to every organizing committee member whose dedication has made this event possible. So I leave you with a one thought. The 21st century will not be defined only by the software. It will be defined by the silicon. It will be defined by the silicon. So, and the future of silicon will be defined by the people who possess knowledge, innovation, integrity, and courage to dream beyond today's possibilities. So, thus, let this summit ignite that journey. Let today's discussion become tomorrow's innovations. Let today's learners become tomorrow's semiconductor leaders. With these words, I declare this one-day summit on Silicon India 2030 VLSI and Chip Design Summit from Design to Fabrication inaugurated. I extend my best wishes for the grand success of this one-day summit. Thank you. Jai Hind. Namaskar.
Thank you, sir.
Thank you, sir, for your inspiring words and constant encouragement. Your vision motivates all of us to strive for academic excellence and innovation. Thank you. Thanks a lot, sir. We now move on to the inaugural technical session of the summit. It is my privilege to invite Dr. Rahul Kumar Gupta, who is an assistant professor, JSS University, to introduce our esteemed guest for today's inaugural session. Over to you, sir.
Thank you, ma'am, and good morning, everyone. My heartfelt thanks to entirely JSS University Management for giving me this opportunity. It is my privilege and honor to introduce our distinguished speaker for today's one-day summit on Silicon India 2030 VLSI and Chip Design Summit from Design to Fabrication. Dr. Rajiv Kumar Ranjan is an associate professor in the Department of Electronics Engineering at the Indian Institute of Technology, IISm Dhanbad, where he also earned his PhD degree. He began his career as a project scientist at CSIR Siri Planning 2004 to 2005, later served as an assistant professor at Slide Punjab 2007 to 2010, and has been with IIT IISm Dhanbad since 2010. He has published over 65 papers in reputed journals, including IEEE transactions on circuits and systems, IEEE transactions on nanotechnology, and IEEE transactions on VLSI systems. His research spans memory strip systems, crossbar arrays, neuromorphic computing, biosensors, analog and mixed VLSI circuits, and CMOS digital design across advanced nodes, along with projects such as smart auto irrigation and soil monitoring. His lab is primarily funded by Ministry of Electronics and Information Technology, MIT. Dr. Ranjan has been featured in the Stanford University Top 2% Scientist list in 2023 and received the Shastri Institutional Collaborative Research Grant in 2020. He serves as an associate editor of Journal of Circuit Systems and Computers, and as editorial manager of AEU, International Journal of Electronics and Communication, while actively reviewing for leading journals. He has also taught a wide range of undergraduate and postgraduate courses in electronics and VLSI design. His integrated circuit EPIC-1, a low-power analog memory star emulator, received national recognition at Semicon India 2025, inaugurated by Honorable Prime Minister Shri Narendra Modi ji, underscoring IIT-ISM Dhanbad role in India's semiconductor mission. There are a lot of media coverages for Dr. Rajiv Kumar Ranjan sir, Times of India, The Delhi Pioneer, Lagatar 24, ETV Bharat, Jagran, Shiksha.com, The New Indian Express, Jharkhand Mirror, Drishti IAS for their projects. And recently, one patent has been granted for auto-irrigation and soil monitoring system, which is developed by IIT ISM Dhanbad. Today's Dr. Ranjan will deliver an insightful talk on memory star technology from theory to practical circuits. The talk will explore the evolution of memory star technology, practical circuit implementation, memory star emulator designs, and their applications in neuromorphic computing, artificial intelligence, in-memory computing, and energy-efficient electronic systems. On a personal note, I feel especially honored to welcome Dr. Rajiv Kumar Ranjan sir. I had the privilege of pursuing my master's degree under his guidance, and I have personally experienced his exceptional mentorship, academic excellence, and dedication to research. It is truly a proud moment for me to introduce my mentor as a keynote speaker at our VLSI Summit. I remember that sir always sit with us online till the morning 2 a.m. and work together in 2020 in Corona period. Thanks for mentoring me, sir. If I say that the one who awakened the research bug in me is my mentor. So on the behalf of all JSS University management, ladies and gentlemen, please join me in extending a warm welcome to Dr. Rajiv Kumar Ranjan sir. Sir, we are delighted to have you with us and the stage is yours. Thank you, sir.
Thank you, Rahul, for nice introduction. So just now I'm going to start my talk. Is it visible?
Yes, sir, it is
Yes, sir.
visible.
Okay.
Sir, can you please on your video?
Actually, I have joined two places. So now, is it visible?
Yes, sir. Yes. Now this is visible.
Actually, if I on the video, there network problem will be there actually some.
Now it is visible, sir. Thank you.
sir. Okay, sir. Okay.
Okay. So if you want to take photograph, then I will switch off the video as per your requirement. Is it okay now?
Okay, sir. Thank you, sir.
Okay, okay. Good morning, everybody. In this talk, I will present an overview of memory star technology, highlighting its evolution from theoretical foundation to practical circuit realization. The session will begin with concept of memory star as a fourth fundamental passive circuit element and discussed its unique electrical characteristics and memory behavior. So I will explain the operating principle, mathematical models, physical implementation of memory strip devices, special emphasis will be given to memristor emulator circuit, demonstrating how theoretical concept can be translated into hardware implementation for experimental studies and real-world applications. Further, I will discuss the role of memristor in emerging technologies, including non-volatile memory systems, neuromorphic computing, artificial intelligence, hardware, adaptive circuits, and low power electronic systems. Practical circuits examples and recent development in memristor based application will be also presented. This talk will conclude with current research challenges for future opportunities and directions of advancing memristor technology towards next generation intelligent electronic systems. So these are my scope of my talk. In this case, initially I will discuss the current mode analog building blocks. So that I will introduce here current mode analog circuit concept and discuss important analog building blocks with modern system design, and their advantage is high speed and low power applications will be also highlight in this first sections. Next is memristor and its properties. So here I will explain concept of memristor and how it is four fundamental passive circuit elements and its key features, key characteristics, memory effect, nonlinearity, resistance switching behavior, and mathematical modeling. Then memristor emulator design using analog building blocks. So in this, here we will present the realizing of memristor behavior through emulator circuit design using analog building blocks, circuit operations, implementation aspects, and experimental consideration will be discussed. Then fourth one is memristor applications. So I will show various applications of memristor technologies, including non-volatile memory, neuromorphic computing, artificial intelligence, hardware, programmable analog circuits, and next generation intelligent electronic systems. So finally, I will provide important research references, relevant development that supports further study and exploration in the field of memristor technology. So initially I will show what is the current mode circuits. Before discussing memristor implementation, it is important to understand the concept of current mode circuits and how they differ from conventional voltage mode circuits. So electronic circuit can be broadly classified into two categories. One is a voltage mode circuits, another is a current mode circuits. In voltage mode circuits, voltage acts as a primary variables, while current plays a supporting role in case of voltage mode circuits. Most conventional analog circuits are designed using this approach. So there are few key characteristics of voltage mode circuits, that is, information is processed in the form of voltage in case of voltage mode circuits, typically offers high voltage gain, more sensitive to parasitic effects, perform may degrade at high frequency, and common example is operational amplifier circuits. You can say 741 is the most important, most popular, this one. Now I'm going to the current mode circuits. In current mode circuits, current becomes the primary active variables while voltage acts as a secondary parameters. So current mode designs has gained significant attention in modern analog and mixed signal systems. So the advantage is higher operating speed and bandwidth, better linearity and dynamic range, reduced influence of parasitic capacitance, lower power consumption in many applications, suitable for low voltage and high frequency applications. These are the key advantages of the current mode circuit. So people are now start doing research in the current mode circuits. So we already discussed, we already seen here current mode circuit signals are normally represented by current. So there are few advantages. So first advantage is is high speed. So current mode circuit generally provides faster operations because current transferring mechanism reduce charging and discharging associated with parasitic capacitance. So this enables rapid signal processing. So due to that reason, the speed of current mode circuits will be more. Now less power consumptions. These circuits can operate efficiently at lower voltage level, resulting in reduced overall power consumption, which is particularly beneficial for portable and integrated electronic systems. Now, third is higher signal bandwidth. So, current mode circuit processing supports wider bandwidth operations, better high frequency performance, making it suitable for communication and real time applications. Then large dynamic range, the current mode circuits can handle a wider range of signals amplitude while maintaining acceptable performance and reducing the distortion of the circuits. Less supply voltage. So one of the major advantage of current mode circuit is compatibility with low supply voltage, and which align well with modern VLSI and CMOS technologies. And last is greater linearity. So current mode circuits often exhibits improved linear behaviors over the broader operating range, loading to improve accurate signal processing and lower harmonic distortion. So overall, these advantages make current mode circuits an attractive choice for implementing analog building blocks and memristor emitter circuits, which are important component of this talk. So now we know that this operational AD844, that is second generation current conveyors, is important one. So the symbol is shown here. Here X and Y is the inverting and non-inverting terminal, and W and Z is the output. So here W and Z is same, only the buffered output is connected here, W and Z. And this symbol is OTA. So OTA is nothing, that is called operational transconductance amplifier. So here beauty of this OTA is you can tune the transconductance gain of this OTA, which is not available in the operational amplifier. So here this IABC is a biasing current. So this through biasing current transconductance gain of this OTA we can tune externally, which is not available in the other analog building blocks. That is main advantage. Now, if you want to inbuilt both property in one analog building blocks, so people have designed this current conveyor transconductance amplifier, that is CC current conveyor plus TA2. So this CCTA will give the benefit of both current conveyor benefit and OTA benefit. So researchers are doing research in this case, or in this way, here two AD844 and one OTA is connected and gives the both the benefit of CCTA. Now next one is DVCCTA, differential voltage current conveyor transconductance amplifier. This is nothing. This is a current conveyor, but input is applied a differential input and cascaded connection of transconductance amplifier. So there are few applications, that is oscillators, filters, amplifier, memristor emulator, and symmetry trigger, and many more of these using these main building blocks. So this is the first proposed by this Cedra Smith in second generation current conveyor plus. So symbolic representation of is shown here. Vx, Vy is the input and Iz is output. So if current inverts to the double C2, so that will give the positive I plus. So here, if you see this port relationship, so Iy equal to 0 because this terminal impedance is very high, so I know current will towards the Iy terminal. So Iy equal to 0, Vx equal to Vy. So voltage, if you apply at the terminal Vy, so that will be copied to the external, and Iz equal to Ix. So its internal structure is shown here. So here Q1, Q2, Q3, Q4 forms a translinear loop. So base emitter junction of Q1 and Q2 is equal. So Vx equal to Vy, and then Iz equal to Ix plus. So current generated at this Q2 terminal is transferring to IC1 due to current mirror using Q5 and Q6. And this IC4 collector current generated by Q4 terminal is transferring to this Q8 terminal, because Q7 and Q8 is forming another current mirror. So hence Iz plus equal to IC2 minus IC4. Here also IC2 minus IC4. Hence we can say that Iz plus equal to Ix. So this is the internal structure, BJT based internal structure of CC2 plus. This is circuit symbol of CC2 minus. So in this case, the internal structure is same and symbolic representations directions is reverse of previous one. So here again Iy equal to 0, Vx equal to Vy, and Iz equal to minus Ix. So in this case, if you see that Q1, Q2, Q3, Q4, which I have discussed in previous slides, the translinear loop, and here to make Iz equal to minus Ix, so we have cut here in the circuit, and another connect two current mirror Q9, Q10, Q11, and Q12. So that becomes cross coupled. That becomes current becomes 180-degree phase shift of Ix. So the Iz equal to Ix. So this is the second generation current conveyor negative, CC2 minus. This is the commercial available AD844. So here commercial available with parasitics. So the RY, CY, RX, RZ, and CZ, these are the parasitics available at the different nodes. This is the pin configuration. So here 2 and 2 is inverting, 3 is non-inverting, 6 is output. So this integrated circuit is monolithic integrated circuit which is available in the market. So from that, researcher will do the different types of research of different types of analog signal processing circuit we can design from this AD844 which is available in the market. Now next is operational transconductance amplifier. So this is the circuit symbol of operational transconductance amplifier. So here I0 equal to GM BP minus VN, and GM equal to K under root 2 VV VSS minus 2 VTH. And here this is the internal structure of MOS based OTA. So in this case, if you see that BPGM current generated at this terminal is BPGM5 and BNGM6. So this BPGM5 is transferring at M9 terminal, and this current is transferring. So here again using M10 and 11 current mirror, and this again is transferring here. So overall, if you see that if GM5 and GM6 is equal, so IO equal to GM BP minus BN. This is the output equation of the CMOS based operational transconductance amplifier. So in case of BJT based, that IB equal to GM upon 2 VT. So here IB is proportional to GM on the case of BJT based. So here GM is equal to K under root 2 VV minus VSS minus 2 VTH. But here also you can change the GM using this application of voltage at the VV terminal. So externally you can tune again transconductance amplifier, and while you will design different types of filters or oscillator, so externally applying the voltage, you can tune the parameters of the oscillator or filters. This is the advantage of operational transconductance amplifiers over the op-amp. This is the commercial available CA3080. This is the BGT based OTA. So this symbolic representation I already discussed. So equation is for this I0 equal to GM BP minus VN, and GM equal to IB upon 2 VT. So here GM is proportional to bias current. So bias current is fifth number terminal which is available in the market, monolithic IC, which is available in the market. And VT is the thermal voltage, which is 26 millivolt. So this is the top view of CA3080. Here, 2 is inverting, 3 is non-inverting, 6 is the output, and 4 and 7 is a voltage, and 1 and 8 is not connected, and this 5th is a amplifier bias, which is used to here to tune the transconductance of OTA. Now this is the actually current conveyor transconductors amplifier. So this is cascade combination of double C2 and OTA, and this block will give the advantage of double C2 and OTA. So this portion is, if you see carefully, this portion is again this double C2 current conveyors here, but here output terminal is J2, J1 and J3. So one terminal is connected to OTA, OTA of one terminal, and another terminal is grounded. So from that, if you see that I0 equal to plus minus GM VZ, so VZ is the voltage at J terminal. So again, if you want to output same with negative sign or 180 degree phase shift, so for that we have people or researchers connect this M28, another M28 and M29 is one current mirror, and M25 and 30 is another current mirror to make I0 plus to I0 minus. So this is the overall double C2 OTA, and this one is the CMOS based current conveyor transconductance amplifiers. Now, due to inability of current conveyor transconductance amplifier, people are doing the research using this 8844 and CA3080 with connections. We do the connections and we will get the port relationship as discussed by CCTA. So practical view means here RYCY, RICI, these are the parasitics available. So which can affect the port relationship value by these parasitics, or non-directly we can say. Another block is DVCCTA. So this is designed again cascaded combination of DVCC and OTA. So here, if you see the port relationship IY equal to 0, IY2 equal to 0, Vx equal to Vy1 minus Vy2, Iz equal to Ix, Iz equal to Ix, and I0 equal to GMVZ2. So this again the combination of DVCCTA and OTA. So transconductance gain here is externally we can tune, and GM equal to K VCC minus VC minus VSS by 2 minus VT. So this you will get from the theoretical analysis of internal block. This is the internal structure of DVCCTA. So this portion is nothing. This is current conveyors, but differential voltage we have applied here, this portion, and then output is connected to the OTA. So that becomes DVCCTA. Now next is so up to the till we have discussed the different types of blocks. People are doing the research in error-free or good results of designing of different types of analog signal processing circuits. Now my talk is related to memristor. So this my talk is not on memristor devices. My talk is on memristor emulator. We are doing the research on the copying of the memristor fingerprints to memristor circuits. So memristor device still not came in the market. So that is not giving the good result. So people are doing the research in the memristor emulator. Emulator means copying all the properties in the circuit. So here, before discussing the memristor circuit, so and applications, let us first understand the origin and basic concept of memristor. So we know that this memristor was theoretically proposed in 1971 by Professor Leon Chua of the University of California, Berkeley. So he observed that among the 4 fundamental electrical variable, voltage, current, charge and magnetic flux linkage, one relationship was missing. So he predicted a fourth fundamental passive circuit element called memristor. Memristor is nothing that is memory with resistance, and its unit is ohm. So after 37 years, in 2008, Stan Williams and his team at HP Laboratories experimentally demonstrated a nanoscale device so that gives the memristor behavior. In this way, so we can say that electrical circuits are four variables, that is voltage, current, charge, and magnetic flux. So current is what? Current is what? Current is I equal to dq upon dt, and voltage is the rate of change of magnetic flux, that is V. V is d phi upon dt here. And this resistance is what? It relates the voltage and current. Capacitor relates the charge and voltage, and inductor relates the magnetic flux and current. How it is? V equal to Ri in case of resistance, Q equal to CV in case of capacitor, and phi equal to Li in case of inductor. So what is missing here? So only missing relationship was between the magnetic flux and charge. This one, red one, missing link. So Chua proposed that relationship should be represented by new passive device that is called memristor. Okay, so now what will be the equation for the memristor? Memristor is defined d phi equal to mq upon dq, where mq equal to d phi upon dq is called memristance, rate of change of magnetic flux with respect to charge. Unlike a resistance, memristance depends on the history of charge that has been followed through the device. Now why it is called memory resistance? The reason is that the resistance changes depending on the direction and amount of current flowing through the device. Even after power is removed, the device retains its resistance state, making it non-volatile memory element. This is important one. Then IV characteristics has a linear IV characteristics, whereas memristor gives a pinch hysteresis loop passing through the origin. This one. At high frequency, this hysteresis shrinks and memristor behaves like a linear resistance like this. So now what is the applications of this time? So memristor are useful in RERM, neuromorphic computing, AI accelerators, in-memory computing, analog computing, FPGA-based system, and low-power edge devices or AI. So we can say that memristor is regarded as a fourth fundamental circuit element. It links magnetic flux and charge. Remember its resistance without power, and is promising technology for a future memory and neuromorphic computing. Now, here this memristor is a non-linear memory with resistance, having unique behavior and characteristics. This is a two-terminal device, and it was element that change its resistance depending upon how much charge flow through it. Its resistance it depend on physical history of the charge, and its unit is ohm. This is general concept of the memristors. Or memristors, you can say, is a resistance, its unit is ohm, and this resistance with memory is included so that it gives the relation between charge and flux, so that is called memristance. Based on this memristor relations, there are two types: charge control memristors and flux control memristors. The equation Vt equal to mqt it and it equal to wqt Vt. So these two types of memristor emulators, researchers are doing research based on this charge control or flux control. So there are few fingerprints of the memristors. So here first fingerprints means unique property. In the loop, current voltage plane when driven by bipolar periodic functions, periodic signals. If you apply the biperiodic signals, so pinch hysteresis loop in the current and voltage plane. This is first one. Lobe area of hysteresis loop should decrease when excitation frequency is increased. That is means if you increase the frequency of the signal, so lobe area of hysteresis loop should decrease monotonically. This is the second one. Pinch hysteresis loop shrinks to a single valued function when frequency tends to infinity. When frequency becomes infinity, so that becomes a single valued function. It acts like a linear resistance at a high frequency. Now, fourth one is memristor also exhibits non-volatile property. Non-volatile means if you apply the signals and you remove that signals, so that value will retain, resistance value will retain. So that is called non-volatile property. So you can say that memristor emulator remains unaltered when no input signal is applied. That is called non-volatile property. So these are the four fingerprints properties of the memristor. So we are this device-based circuit, this property we are replicating or copying to the chip or integrated circuits. So what are the advantages? So memristor are very comfortable with interface with CMOS technology. It does not use any power. So it consumes less energy for generating less heat. It has high storage density and high switching speed, and it has capability to memorize the charge, a flow of charge in a set of time. Now, so these are the advantages which we have understood about the devices. Now, what is the need of memristor emulator? So there are few 3-4 points. So due to that reason, people are working on the emulator or memristor emulator. So here is one. So emulator is what? Emulator is mimic of characteristics of memristor. This is the first one. So next one, nanoscale memristor have high frequency, high fabrication cost, technical difficulties in production. So in the memory strip device case, compatibility with CMOS technology, emulator you can easily compatible with CMOS circuit, and is simple to develop precise spice macro models, and dynamic behaviors of memory emulator can be modified so as to explore the design issue and potential applications. Means you can tune, externally you can tune the behaviors, so easily you can fit in any circuits. So due to that reason, people are working in the memory strip device circuit, and people are tape outing that circuit and fabricating the integrated circuits IC. Now, first memory strip emulator is this one, CCTA based memristor. So here in this circuit we have used a CCTA. This circuit works as both and grounded and incremental and decremental, and it can operate up to 1 megahertz of the circuit. So this is the theoretical analysis of the CCTA based circuit. If you see this circuit, so here input voltage V in T equal to I in T R1 plus Vx. So using we know the port relationship which we have already discussed, Vx equal to Vy and I0 equal to plus minus Gm Vz2. So Vx equal to Vy equal to plus minus I0 R2, and here R2 is here, and this I0 equal to plus minus 2k V1 plus Vss minus V2 Vz2. So this is Vx and Vy, means voltage applied at Vy terminal is copied to the Vx terminal. This is the property of current mode circuits. On substituting, we get Vz2 equal to INT R3 equal to K mu x Ux W by L and V1 equal to QCT upon C. So hence MQCT equal to V in T upon I in T equal to R1 plus minus 2K R2 R3 VSS minus VT plus minus 2K QCT C R2 R3. So this is the memory distance equation. So this term, if you see, this is the fixed term. So you can change this term. So this will give the memory effect of memory stimulator circuits. Now this term is time varying term. So if you apply input voltage V in T equal to AM sine omega T, so this average input current IT equal to V in T divided by R1 plus 2 K R2 R3 VSS minus V2, and QCT we know that this 0 to T INT. So charge is given by this one, QCT equal to AM divided by omega R1 plus minus 2 K R2 R3 VSS minus VT into cos omega T plus phi. On substituting this value in this previous equations, MQCT equal to V in T upon I in T. So that becomes linear time invariant parts. So that is constant term, which is R1 plus minus 2K R2 R3 VSS minus VT plus minus 2K R2 R3 AM divided by omega C R1 plus minus 2K R2 R3 VSS minus VT into cos omega T phi. So this is the time varying parts. So this will give the memory effect in the memory stimulator circuit. Using this non-ideality analysis, so we have Iy equal to 0. This equation is not Vx equal to V beta time Vy, because this output is not directly come to Vx terminal. So this value we have applied in the circuits. So these are the different equations of incremental and decremental memory stir with effect of non-ideality included. Now, so we also people researchers are doing the research in the simulation labs. So we get these simulations of the theoretical concept. So here you can see the 10 hertz, 50 hertz, and 100 kilohertz. So while frequency is increasing, so low area is decreasing. So this justifies the fingerprint of ministers. So this is for incremental switch to HRS and decremental for switch to LRS. So these two are the simulation result of the CCTA based memristors. So here this pinch resistance loop is showing the omega C is constant in the both the case incremental and decremental case. Incremental means directions of currents, and directions of current is showing incremental, or the reverse is showing the decremental case. Here, when capacitor value is decreasing, the low area is also decreasing. So this you can say for incremental topology and decremental topology. Now, to verify the circuits using macro models which is available in the market, so people are doing research, and PCB designed some emitter circuits using AD844 and CA3080 is shown here, and this is the circuit design, and this one is the we have done in the laboratory, and experimental result is seen. So that experimental result is shown here. So here component is used R1 equal to R2 equal to 10 kilo ohm, R2 equal R equal to 22.2, and R4 equal to 1 mega ohm, V equal to plus minus 10 volt, and AM equal to 4 volt. So the at frequency 5.16 kilohertz, C equal to 10 nanofarad. So these loops we have observed in our laboratory, and at 30.4 kilohertz we observed this output. So you can say when frequency is decreasing, so low area is decreasing. This was the CCTA based. Now next one is DVCCTA based memristor emulator. So here memristor emulator is used only one single DVCCTA, which is charge control memristor, and here one DVCCTA, 3 resistance you can see, and one capacitor used. This shows the non-volatile property and configured incremental and decremental by interchanging these connections, and operate at 1 megahertz frequency. Now, if you do the routine analysis, So V in equal to I in T R in plus Vx. This is equation 1. So Y1 and Y2 terminal is connected at this terminal. So Vx we will get this one. So equivalent memristor after the routine analysis, we get MQT equal to R in minus plus K minus VSS by 2 minus VT R1 R2 minus plus K R1 R2 QT divided by 2C. So this portion again time invariant, and this is for the time varying parts of the memristors emulator circuits. Now we have also done the similar analysis in our laboratory. So we got this 25, 50 and 100 hertz. So 100 hertz pinch resistance area is sinking. So that justify our memristor is working. This is for the C equal to 100 nanofarad, and this previous one is C equal to 1 microfarad. Now omega C is constant. So here all the loop coincides. Area under pinch resistance loops remain same. So this is this showing here. So this one is showing the non-volatile property, means here if you apply the one signals and then there is no signal in between. So this value is written, and that is the memristance value, so that we can use any different places. So this is for the incremental, and this is for the incremental case. We took that, and researcher have done this kilohertz this pinch resistance loop and 100 kilohertz this pinch resistance loop of this memristors DBCCTA based memristor emulator output. Third one is flux control memristor emulator. So here again 2 blocks have used. Both works as a incremental and decremental and can operate up to 25 kilohertz. So routine analysis from the circuit, you can easily see Vx equal to Vy equal to V in this case, and Vz equal to V equal to phi upon Rc. So hence In equal to K under root 2 phi Rc minus VSS minus 2 VTH. So this is the circuit. So here in this case, memductance, we got In upon Vin is equal to minus K under root 2 VSS plus 2 VTS plus K phi upon under root 2 RC. So this is the memductance. That is not a memristance. That is reverse of that one, memductance, you can say. So routine analysis, we got this memductance equal to minus K under 2 VSS plus 2 VTS plus K AM cos omega T minus pi divided by 2 under 2 pi FRC. So this one is time varying parts, and this one is time invariant part. So this is the memductance equations. So after considering the non-ideality, so this becomes K gamma under 2 VSS plus 2 VTS plus K alpha beta gamma 1 fine at under 2 C plus CZ and R plus RX. So this is the memductance considering the non-ideality and parasitics effects. This will researchers have obtained these equations. Now after the simulation result, we got this analysis of the circuit. So 400 kilohertz, 500 and 600. This one is shown. For another one, we have also simulated to 1.2 megahertz. So this is the output simulated repair using Cadence Virtuoso tool. So this one is for different value of C for 2 picofarads, 0.98 picofarads and 0.5 picofarads. So the capacitor value reduces in order to hold the hysteresis loop at higher frequency. Low area decreases with incremental of frequencies. Now different value of capacitor maintaining constant frequency is shown here. Here low area is decreasing with increment of capacitor value because capacitor value is denominator term. So this is for the 500 kilohertz and 1 megahertz. Here omega C is constant, so all hysteresis loop curve coincide localized and phi remains unaltered. This we also analyze for the temperature analysis. So this is different temperatures value. We got the different temperature loop, and here FF, TT and SS we have done is various temperature and process corner. So here this graph is different process corner. So less current flow in SS process corner, while more current flow in FF case. So here this is showing the non-volatile property in incremental case and decremental case, and this pulse strength is applied to obtain the non-volatile property. So here memductance is non-volatile and its variation is negligible in non-pulsate period. So same memdactance is preserved. So this is the pre and post layout simulation result of the circuit. So you can see that to check the parasitic effect, the overall performance is showing. So effective area is 75 micrometer to 70 micrometer. Now we have also done the experiment of the circuit in our laboratory. So here IC we have used 8844 and CA3080 and supply voltage is 10 hertz. So it performs 400 kilohertz, 800 and 1 megahertz and 1.4 megahertz. So 400 kilohertz we receive this type of pinch stage loop, and in 800 kilohertz is this type of pinch stage loop. So also we have observed up to 1 megahertz this type and 1.4. So we have observed distortion have been observed on the further increasing the frequency, and loop becomes deformed using resulting asymmetrical behaviors, and loop becomes normal when frequency is increased. So this output purely justify the theoretical concept of memristor emitter. Hence our simulation as well as experimental result is verified. Next is charge control memristor. So here we have used CC2 and CCTA. So port relation is shown here. So it works up to 5 megahertz. So this is floating type memristor. So the routine analysis is VA equal to INTR1, VB equal to these equations. So hence VA minus VB is this potential. So MAB divided by current. So R1 plus minus K R2 R3 VSS by 2 plus VT minus plus K R2 R3 QCT by 2C. So this is the memristance of this floating type memristor emulator. So frequency analysis of the circuit, we got this term is time invariant parts, and this is time varying parts. So this portion is constant term and this portion is variable term, that will give the memory effect of the circuit. So this is the simulation result. So here capacitor value has to be reduced for holding the hysteresis loop at high frequency. These two different level of omega and C is obtained of the circuit, and different value of different loop obtained of different value of frequencies. This simulation is performed of omega C is constant. So here all the hysteresis loop coincide and look alike, and phi remains unaltered in this case. This is different value of capacitor maintaining constant frequency. So low area is decreasing with increment of capacitor value. Now non-volatile is also verified. So here this pulse is applied, and this portion one pulse is applied, and here also applied. But this portion is no any pulse is applied. So you can see that this portion is 225.5K is memristance value is retained. So this is for incremental case and this is for the decremental case. Using commercial available IC, we have also experimented. This one is experimental result, and this macro model with experimental result component value is shown here. Now, so we have seen here three different types of memristor. Now memristors are applicable in RLC and analog filter applications. Memristor can use in the non-linear circuit like Chuaj circuit design, low power applications, storing analog signal processing. Memristor are also used digital memory, logic circuits, and neural network and neuromorphic systems. There are these type of applications of the memristor emulator circuits. So we have also applied this memristor in one RC filters. So you can see this output of cutoff frequency, and F3 dB is shown here. So easily you can tune the cutoff frequency using OTA based memristors. Now memristor as a amplitude modulation for FM signal. So here V in is here and V out is here. So here G, you can see that minus R1 upon Rm. So here Rm we have changed. So accordingly gain will change. So this will give the FM input is applied and amplitude output we have received. So output we can see this one. So at high frequency, so amplitude is more. So this circuit is works as FM to AM conversion. And then this circuit will give the detected output. So this overall application is showing of the memristor. The next is memristor emulator for spiking signal generation in the neuromorphic applications. So here, this is again this CMOS internal structure. This we have already discussed. So now this is memristor emulator using OTA and CMOS inverter. So here CMOS inverter and OTA we have used. So routine analysis we have done is theoretical concept using this IZ we know that, and GM we know. So using this we have derived the memristor equations. This one I in upon V in, that is and that is not a memristor, that is memdactance, which is K under 2 find GM upon C minus Vs minus 2 VTS. Since Vs is ground, so hence memdactance is given by K under root 2 find GMC minus 2 VTS. So this is the memdactance of this circuit. So I'm not going detail in theoretical analysis due to time constraint, but if you do, so you will get these equations. Simulation result we have also done. So this is the simulation of OTA, and aspect ratio is this one, and we have used 0.18 micrometer CMOS UMC technology. So these are the analysis of circuit simulation results of our OTA, and this one is also. So here PHL of 10 megahertz we have obtained. You can see this one. So here voltage we have set this reset voltage, set voltage is this one. This is the simulation result of 5 and 10 megahertz. This is FFSS and nominal values. This also we have done is noise analysis also. This is the non-volatile property. So you can see if there is no pulse, then this value is retained, memdactance value. So this is the layout of the memristor circuits. So here this is the post layout result. Then layout area is 7452.52 micrometer square, and this is the pre and post layout overlapped. So this is showing some characteristics due to non-identity. So this is the fabricated IC at macro UMC IMEC Belgium. The layout area is 745.52 micrometer area. Die size 1499.96 micrometer cross 1499.96 micrometer, and the pins is 44. So we have fabricated this this memristor emulator, and this is the chip macro graph of the circuit. Though this circuit, this memristor emulator circuit, we have tested in our laboratory. So this fabricated memristor emulator chip is shown. This fabricated result is showing. This is the pinch hysteresis loop at low frequency. This high frequency, this showing the at high frequency at 50 megahertz PHL is decreasing. This one is for 10 megahertz. This one is 5 megahertz. So this is the output of this memristor chip. Now we have also took the value of data, and this is the simulation result and experimental result of this data. So this is experimental simulation, 3 different frequency, 5 megahertz, 10 megahertz, 50 megahertz. Is this experimental results are from our fabricated memristor emulator chip using 180 nanometer technology of UMC. Now that application is this is the LIF and this is the MIF. So if we include here the memristor in this case, so number of transistors is reduced. So this is the again current mirror integration and symmetry trigger. So this is the MRE, so which we have fabricated, that we have included in the memristor integrated and fire neurons. This is the again the same circuit. So here we have analyzed the power consumption 19.6 macrowatts, energy per spike 196 picojoule, and static power is this one. So here current mirror, integrator, symmetry trigger, and reset control. These are the 4 units. So reset control is provided by our memristor emulator circuit, and simple RC circuit is parallel with generator refractory period. So here is the W/L ratio, which is used in the designing of signal of different value, input spikes and output spikes. Is in here these three different. So this is the magnified output. This is again so magnified output and different value of capacitors. Above nature of the spiking neural shown is dependency of capacitor CM. This is also state voltage evolutions in output spikes is red one, and this is the state voltage evolution signals. This is input spikes, then this is the output spikes. So in this case, we have how to generate the pattern. So C, we have this one, and this is for I, and this is for F, and this is for P. Weight matrix we have calculated and we have done it. So now this is the MIF neuron crossbar systems. So you can see that this for C output, this is the output, and this is for C, this is for F, and this is for I, and this is for P. So this is the designed MIF neuron crossbar array. Here we have area is 250.48 micrometer cross 39176 micrometer. Average power consumption, energy consumption is 5.255 picojoule. Total neurons is 48 in this layout. Power supply used is plus minus 1.8 volt. So this is the layout of MIF neuron crossbar of this one. Now this is the simulation result. So here pixel marks a green has low voltage and hence fails to charge CM. Pixel marks in blue has high voltage and hence charge to CM. Each summed current at the respective column has different voltage level. So these are the output of different pixels. Now this is the simulation result. So the successful learning as per train pattern can be easily validated through inspection of output voltage. Spikes at their respective output terminal out 1, out 2, and out 3. Further, the pre and post layout for output of C and out 1 is shown here, this one. So these are the few references which we have used to preparing the PPT. Thank you. Then ask any questions and any queries.
Good morning, sir.
Yes.
Very vast knowledge of Minister I learned from this session. Thank you for this uh, giving the teaching and learning of this topic. My question, Minister, is that this Minister, I'm also working in the same topic, and I think that the device level implementation, when we can expect this come into a device level, because we now this time research and more research are going on, and this is also thankful that you have implemented one IC for this. But when we will
I have implemented total 6 to 7 IC tape out and fabricated 4 to 5.
Very good, sir. Very nice, sir. So,
But
when this
in
will
this
come into the
case,
device level,
device is very difficult actually. After some few cycles, it is burning. So one Shubham Saha in IIT Kanpur is doing research in device, but they are telling that it will be very difficult to get it.
okay, sir.
Any other?
Any question from audience side?
Sir, I have a question.
Yeah.
Sir, can Memristor will be the new revolution for the semiconductor industry?
Yes. Memristors we can use many places. So we can fit in also. People are doing research and fitting in the CPU design. Okay. So emulator is more scope because device is not successful now. So Mr. Emulator and chip designing have more scope, and you can do research and people can benefited from that one.
Thank you, sir.
Any more?
Good morning, sir.
Yes, yes.
Sir, how do sneak path current affects the accuracy of large memristor crossbar arrays, and what techniques are commonly used to mitigate them?
Actually, different types of mitigate there, but this question is not mostly related to circuit cases. So many techniques you can mitigate that one. In the circuit case, it sometimes comes, but lots of techniques you have. So separately you write email, then I will discuss about that one, how you can remove the scenic path. One paper you can study of my macroelectronics journals. Okay, so there we have mentioned how we can remove the scenic path of memristor.
Thank
Understood?
you, sir.
Okay.
Yes, sir. Thank you, sir.
Oh.
So there is no question, I think now.
Okay.
Thank you very much, sir. So now I will request Rahul sir to give a thank you for this session.
Okay, so respected dignitaries, faculty members, and dear students, on behalf of the Department of Electronics and Communication Engineering, JSS University Noida, I sincerely thank Dr. Rajiv Kumar Ranjan sir for delivering an excellent session on memristor technology from theory to practical circuits. Sir provided valuable insights into the fundamentals of memristor, block-based memristor emulators, and their practical applications in modern electronic circuits. His expert guidance and practical approach made his emerging technology easy to understand and highly inspiring. We are truly grateful for your valuable time, knowledge, and continuous support. I also thank the JSS University Management, head of department, faculty members, and all the participants for making the session a great success. Thank you, sir, and thank you all.
Thank you, Rahul.
Thank you, sir.
Thank you. Now I'm leaving. Okay.
Okay, sir. Thank you, sir.
We now move on to our second technical session of the summit. It is my pleasure to invite Dr. Pooja Pandey to introduce our distinguished guest speaker for this session. Over to you now.
Thank you, ma'am. It is my pleasure to introduce our distinguished speaker, Dr. Kushwant Sehra. Dr. Kushwant Sehra is an assistant professor in the Department of Electronics and Communication Engineering, Faculty of Technology, University of Delhi. He received his BTech in electronics from the University of Delhi in 2017, completed his MTech in EC department from Guru Gobind Singh Indrasta University in 2019 and earned his PhD from the University of Delhi in 2025. His research focuses on the development of GaN HEMT technology with a specialized interest encompassing solid-state physics, device modeling, semiconductor technology, and the simulation of GaN-based HEMT for high power and MM-wave applications, emphasizing GaN HEMT robustness for space application. He is an active reviewer for prestigious journals including IEEE Transactions, JED, and PSSA. Dr. Sehra has co-authored over 25 publications in an high-index journal and was twice selected for the prestigious IAS, INSA, NASI Summer Research Fellowship in 2016 and 2018. Please join me in extending a warm welcome to Dr. Kushwant Sehra. We are pleased to honor to have him with him today and look forward to an insightful and inspiring session. Over to you, sir.
Thank you, ma'am. I hope I'm audible.
Yes, sir, you are audible.
Right, I'll start sharing the screen.
Sir, can you on your video, sir?
Yeah, I hope the screen is visible.
Yes, sir.
Right. Just a sec. Yeah. A very warm welcome and good morning to all the participants. So I would like to thank Dr. Yadav for such a wonderful introduction and Dr. Chandra Shankar for inviting me to this one-day summit. on Silicon India 2030, which is being organized by GSS University India, Noida. And the theme of this one-day summit, Silicon India, is rightly captures the government's push towards the Indian Semiconductor Mission 2.0. So my talk will be a little bit different from the general theme of this one-day summit, as I will be discussing about a new class of materials and the devices, which is the gallium nitride-based HIMS, which are now dominating the silicon-based electronics for high power and high frequency applications. So to discuss about the agenda, I'll be starting with a brief introduction to the gallium nitride. We'll be discussing about the need for switching to a wide bandgap semiconductor. I'll be talking about how gallium nitride as a material has several advantages over the traditional materials that you might have come across. We'll be talking about the issues with wide bandgap semiconductors with regards to the doping. Then I'll move over to the heterostructure field effect transistors, polarization, and then I'll discuss briefly some of the work that I've done in that domain. So if we look at this graph, which basically gives you the breakdown field as a function of the band gap energy. So if you focus on silicon right here on the bottom left corner, you see that the silicon the band gap energy is about 1.1 electron volt, and the corresponding critical breakdown field is around 0.3 megavolt per centimeter. So what this graph tells us is that as you are able to tap on to the materials that have a higher or a wider band gap, you will be able to achieve materials that can support high orders of field. So this relation, it follows what is called as the power law relation. And if you focus this green graph over here, you can see that gallium nitride and silicon carbide are among the commercially available materials that I can say that support a very high breakdown field, about 3.3 megavolt per centimeter. So what that means is, if you are able to tap these materials for making out your devices, so these devices will be able to sustain high orders of field applied bias, and you can scale it down without worrying too much about the breakdown aspects, and in a way it leads to what is called as an efficient power conversion. So gallium nitride and silicon carbide are the commercially available materials. Of course, we do have research grade devices such as the aluminum nitride, diamond and gallium oxide, but the research is still going on in that domain because of the compound stability. So most of the discussions throughout my presentation will be focused on gallium nitride and a bit towards the silicon carbide. So if we look at this table, it basically compares the intrinsic properties of the gallium nitride with commonly used materials. So I'll highlight gallium nitride here. So first and foremost, we see that gallium nitride has a wider band gap compared to the silicon and gallium arsenide. And so this opens up multiple avenues. So with the wide band gap semiconductor, of course, coupled with a high critical field, as you can see right here, this enables you to make devices that can sustain high temperature environment, high voltage that we have just discussed, and because of the strong covalent bonding nature, so these devices can sustain even harsh environmental conditions and are of interest for the space electronics. Low dielectric permittivity, as you can see right here, is essential if you're talking about these devices for application towards RF applications. So a lower parasitic ensures that the transit time of the carriers is not affected. And then that, coupled with the high carrier mobility and high saturation velocity, which what propels these devices to be used for high frequency applications. Now, people may argue that, of course, the gallium arsenide has an even high carrier mobility than gallium nitride, but the applicability of gallium arsenide is limited because if you see the critical field is around only 0.4 megavolt per centimeter. Then there's another important factor that for the gallium nitride, which is the thermal conductivity. So the thermal conductivity of gallium nitride again is very high compared to both silicon and gallium arsenide. So that allows you to scale down the devices without worrying too much about the electrothermal aspects. And of course, so the idea is if the material is having a better or high thermal conductivity, it is basically a testament of how efficient the heat extraction is there. So we need materials with high thermal conductivity at the same time a high band gap and high critical or high carrier mobility. So to be able to tap into high frequency, high voltage regime. So this is just a snapshot that I'm showing here, taken from ST Microelectronics. So on the left hand side and the right hand, there are two boards. So this section here is driven by a silicon-based transistor, and this section here is driven by a gallium nitride-based transistor. So this is just depicting the circuit that is being made at, let's say, for operation at 100 kilohertz, and on the right hand side, the circuit is similar, but it is just scaled up for to operate at 1 megahertz. So the first thing that you see here is the drastic reduction in the transformer size. So it amounts to about 70% reduction in the volume of the transistor, and that follows your Faraday law. So if you increase the frequency, so your the magnetic core will shrink down. The thing that I want to discuss here is so this is just a depiction, a schematic depiction of how the transistor scales down. The main thing to discuss here is, if you look at on the left hand side, so this is basically focusing on the section that has been driven by the silicon based transistor. You can see that the peak channel temperatures, or the peak temperatures across the entire chip, the thermal hotspots, it can reach as high as 125 degrees Celsius. But on the other hand, when you are talking about the gallium nitride, you see the gallium nitride is relatively cooler at this region, and the hotspot, the peak channel temperature that this chip is hitting is only 111 degrees Celsius. Now, this is very important because as you keep on scaling the device operation to higher frequencies, since the silicon-based transistors are not able to cope up with with a fast-changing signal, so the conduction losses increases. So when the conduction losses increases, it will be manifested as heating losses. To look deeper into the silicon and gallium nitride based transistor arrays, so you see here on the left hand side, you can see the peak channel that is touching here is around 120 degrees Celsius, and while for the gallium nitride, it is only around 64.4 degrees Celsius. So that is the kind of advantage we are talking about when we are switching to gallium nitride based devices and gallium nitride material as a whole. So based on this discussion, what we are seeing is that among the commercially available materials, of course, so gallium nitride is the material that stands out as the one which is having a higher band gap energy, higher critical field, and higher saturation velocity, and is therefore an ideal candidate to be used for either high voltage, high temperature, or high frequency applications. So this discussion was with respect to the intrinsic properties of gallium nitride. But to have a perspective from an application side, if we, let's say, talk about some different figure of minutes. So first is, let's say, the Johnson's figure of minute. So the Johnson's figure of merit is a figure of merit that basically characterizes the efficacy of any material to be used either for handling maximum voltage or higher transit frequency. So if you go ahead and do a spider plot, and the value is being normalized with respect to the gallium nitride, you can see that the value of gallium nitride is very high compared to both silicon gallium arsenide. So that gives you an idea that gallium nitride as a material can be optimized for either handling a higher voltage or can be used for transitioning to a higher frequency. Now, of course, the research grade devices are there, aluminum nitride and diamond, so the values are comparable to the gallium nitride. Next, moving on to the Baligas figure of merit. So the Baligas figure of merit quantifies how well the material can be used for switching applications and depends on the maximum handling voltage and conduction losses. So it is roughly given by the square of the breakdown voltage to the onset specific resistance. So if we consider normal semiconductor bar, you dope it and you do some Poisson analysis, you see that the Baligas figure of merit actually depends on this factor. So if you take this factor right here, so you see that this factor, this Baligas figure of merit, is basically dependent upon the third power to the critical field. And as we have discussed right now, so gallium nitride as a material has a very high critical field compared to both silicon gallium arsenide, so it is bound to have a high Baligas figure of merit. So again, this points towards the fact that GaN as a device can also be used, it can dominate silicon for the power switching applications, and is therefore being used currently for different industrial applications, including the EV industry. And then, of course, we do have aluminum nitride and diamond, where people are still working on to make the compound stable and make the devices stable. So based on all these discussions from the intrinsic properties and from the figure of merits point of view, we have observed that gallium nitride as a material is very promising or ideal candidate for different applications, which concerns defense and space sector. But the issue is with respect to the availability of free carriers. For example, if we talk about silicon and if we talk about the N and the P type dopant, for example, if we want to make a simple P-N junction diode, right? So for both of the dopant atoms, you see that the activation energies are comparable with the thermal energy, right? So what will happen? So even at a room temperature, you will have sufficient ionization to give you some free carriers that can give you some meaningful conduction. But as you go on towards the wide bandgap semiconductors, specifically if you talk about, let's say, the p-type dopants, let us take, for example, that we want to make, let's say, a p-n junction diode out of gallium nitride. You see here that for realizing a p-type doping in a gallium nitride, you need magnesium, which is the compatible dopant for gallium nitride. And the issue here is that the activation energy for this magnesium is relatively deep compared to the earlier dopants that we have discussed. So what that means is, if you're talking about room temperature operation, you will have less than 1% of free carriers that are available for any meaningful conduction, and therefore these devices inherently cannot be, exploited to make any transistors out of the box. So the other question is, you might say that, okay, so what we will do is we will increase the doping concentration, but increasing the doping concentration have other implications, as you can see right here. So you can have Coulombic interaction, which will lead to scattering, and therefore again the carrier mobility will get affected. So having a good figure of merit and having a good intrinsic property does not necessarily guarantee that the material will be so successful. So as we see here, so these devices or these materials, I can say that they lack from free carriers, and therefore we need to find some solution out of this, which is where the high electron mobility transistors came into the picture. So the genesis of the high electron mobility transistors was a heterostructure fit. So the idea was simple, to go for a heterostructure arrangement to create something called as a two-dimensional electron gas. So I'll come back to what 2DEG is, this two-dimensional electron gas. So let us consider a basic heterostructure system. So it has a dissimilar band gap energies. On the right hand side, you can see here you are talking about the gallium arsenide, which has a band gap energy of 1.5 electron volt. And on the left hand side, you have the aluminum gallium arsenide, which has a band gap of about 2.2 electron volt. Now, this band gap is tunable depending upon how much mole fraction of aluminum you are providing during the growth. The point here to discuss is that when you go for this kind of arrangement, of course, the Fermi level alignment will take place initially. So if I draw the band gap energy, so this is just the resulting final conduction band and valence band depiction of the AlGas gas system. So I'll remove the unwanted things, but to focus here, like we discussed, so the free carriers were not there. So in order to induce free carriers, what we do is we dope the aluminum gallium arsenide with silicon. Now, the table that I showed, the activation energy of silicon is 0.006 electron volt. So at room temperature, it will give you sufficient free carriers for conduction. So what will happen is, so all the carriers that get generated over here, they will move to this gallium arsenide section because of a lower energy state. And at the same time, they will result in a generation of a localized field that will keep them in position here. So all the carriers that get generated at this section, they will move here, but they are bound here because of the electric field with respect to the mobilized positive ions here, and they're not able to go into the bulk of the gallium arsenide. So this is what constitutes the channel in case of a heterostructure field effect transistor. But the issue here is, again, so this channel that we have developed is with the help of an external dopant. So again, so when you dope it, so the temperature dependency will come into the picture, and temperature dependency will if the temperature dependency comes into the picture, the stability of the device will get affected. So people have studied different designs, different complex designs. For example, the delta doping, where instead of doping the entire gallium arsenide layer, they dope only a section or only a layer uh, in the aluminum gallium arsenide layer. But again, so the doping profile becomes a bit difficult to control. So we had to again find out some different solutions. So the solution was to use a polar semiconductor. By polar semiconductor, I refer to the gallium nitride. Now, the polarization comes here due to the fact that, if you know that the nitrogen here has a more higher electronegativity compared to the gallium. So of course, what it will do is it will try to attract the electron cloud towards itself. So when there will be a charge separation, there will be a polarization field that gets developed in absence of any external field that you are applying. So just to depict in terms of the lattice structure, so you have a gallium nitride here, for example, and you have an aluminum gallium nitride over here. So the nitrogen will try to attract the electron cloud. So there will be a polarization field that gets developed here. So so the direction, as you can see, is here, and it is applicable for both the aluminum gallium nitride and gallium nitride. And then you see here you have instead similar to the aluminum gallium arsenide system, you have a aluminum gallium nitride here. So to decide on the mole fraction, so you have a graph which basically relates the band gap energy with the lattice constant. So I'll talk about this in a while. But before that, if you look at the spectrum right here, so roughly from around 1.8 electron volt to about 3.2 electron volt, you can see that it covers this Vibgyor spectrum, right? And talking about the compound, so you are having gallium nitride right here, which has a lattice constant of about 3.2 angstrom. And if you move along this red line here, so if you add indium in this during the growth, you see that you are reducing the band gap energy. So it is indium gallium nitride. So from binary, you are moving toward the ternary compound. And in between this transition from gallium nitride to indium nitride, you see that it crosses this entire spectrum. And this concept is exactly what this is actually called as band gap engineering, and this concept is what was exploited by these three gentlemen, Izamaku Akasaki, Hiroshima Namano, and Shuji Nakamura, for inventing the first ever efficient blue light emitting diodes, which led them to win the 2014 Nobel Prize in Physics. So this is just a schematic in their presentation. So you can see, so there are multiple layers, of course. So we just need to focus here. So you can see here. So they are using that InGaN layer to have that highly efficient blue LED. And just to show you how it looks, so this is a blue LED on my index finger. And on the right hand side, when we were measuring it, you can see just how bright it is under looking under the microscope. Right. So coming back to the band gap engineering concept. So indium, we were moving down for AlGaN. So when you add aluminum as a dopant during the growth, you see that this follows this blue curve right here. So depending upon the mole fraction of aluminum in this compound, you can transition from gallium nitride to aluminum nitride, which has a maximum band gap of about 6.2 electron volt. During this transition, you see that as you keep on increasing the aluminum mole fraction, the lattice constant of this AlGaN is smaller compared to the gallium nitride. So it has a smaller in-plane lattice constant. So what will happen? So the gallium nitride, so the lattice constant of the AlGaN is smaller. The lattice constant of the gallium nitride is on a higher side. So the underlying gallium nitride will try to rip apart the AlGaN that you're putting on top of it. So that will exert a tensile strain on the aluminum gallium nitride, and this is similar if you can visualize it. So what will happen is it will try to bring these aluminum or gallium towards the interface. It is just similar to if you hold out your shirts and if you just stretch it out, you will see that it collapses at the middle. So that introduces another polarization vector, which is called as the piezoelectric polarization again. So now if you see, for this layer, AlGaN layer right here, the total polarization is the sum of the spontaneous polarization, which was due to the nitrogen electronegativity, and the piezoelectric polarization that is coming because of the strain that gets developed. So as a result, what happens is there will be a polarization discontinuity right here at the interface. So because this value will be a little bit higher compared to this, so what will happen? There will be a positive polarization field that exists over here. Now to talk about it, we are not applying any external forces. There's no external field that is applied. There's no external bias that is applied. So under absence of any such external perturbation factors, we want, of course, so it needs to be electrically neutral, which for right now it is not, because there's a positive field that is present, right? So how the electrical neutrality is, or the charge neutrality is maintained? So when the growth process of the aluminum gallium nitride is completed, we see that the interface of the or the surface of the AlGaN has a very high density of dangling bond. Now these dangling bonds behave like a donor-like surface states. So what they do is they donate electrons, and all the electrons, they will come and get accumulated at this interface. So they will maintain the charge neutrality, and at the same time, they will form the channel, which comes to be known as the two-dimensional electron gas channel. So to talk about what happens from a band formation perspective, so on the left-hand side, you have the aluminum gallium nitride. On the right-hand side, you have a gallium nitride. So first, what will happen? So the Fermi level alignment will take place, and then the conduction band needs to be continuous. So this is the band bending you observe. And then finally, the surface states from this surface will come, and they will get accumulated right here at this point. Now, For the algan-GaN system, because there was a positive field here, that is what is keeping those electrons fixed at this position. So again, what will happen? These carriers cannot break free from this confinement and they cannot move into the bulk of the gallium nitride layer, nor they can move back to the algan layer because of this barrier that gets developed. Now, this channel that gets formed is basically called as the two-dimensional electron gas. Now, the reason why it is being called as electron gas is if you can imagine. So the carriers, they are situated at this interface right here. They cannot move into the bulk. They cannot move to the algan layer. So they are tightly confined in this two-dimensional space, and the only place where they can move is inside and outside this plane. So that is the reason why this is called as a two-dimensional electron gas channel, and this is the quantum channel which gets formed only by placing the algan on top of the gallium nitride layer. So just for a comparison, if you look at the gallium arsenide that we had discussed initially, so we had to dope it externally with respect to the silicon atom in order to induce some free carriers. And the density, or this is basically called as the sheet carrier density, so that was 10 to the power 12 electrons per centimeter square. For the gallium nitride, it is higher, 10 to the power 13 electrons per centimeter square in absence of any doping. So this is sometimes also called as unintentionally doped two-dimensional electron gas channel or two-dimensional electron gas region. So talking about the general architecture of a HIMT, so high electron mobility transistor. So starting from the substrate, you have for this architecture generally we go for a silicon carbide substrate. You starting on the substrate, you have something called as a nucleation layer. Now, depending upon the kind of substrate that you're using, the definition of this layer or the role of this layer changes. So for in case of silicon carbide, you have an aluminum nitride, which is called as a nucleation layer, because this basically gives you the nucleation sites for the subsequent growth of the gallium nitride layer. Now, this gallium nitride layer, along with the algan layer, is what we had discussed right now, which results in the generation of that two-dig channel. Now you will see that there is an extra layer that gets added between these two layers, which is called as the aluminum nitride spacer layer. So the idea behind the spacer layer is, if I go back to this band, so this, if you focus right here, so this is similar to any physics potential problem that you must have solved. So you have a finite potential well, you have infinite potential well. So for this system, this is let us approximate it by a triangular potential well. So when you go ahead and solve the Schrodinger equation, you will find out that the wave functions, which is basically the probability of finding an electron, it will not terminate exactly here at the boundary. So there is a possibility of finding the electron in the algan layer. So in order to prevent any carrier overspill back to the algan layer, you add a thin aluminum nitride layer over here. And like we have just discussed, aluminum nitride has a wider band gap, so it will raise this barrier even further, so that the carriers cannot go back to the algan layer. So it improves the carrier confinement at this region. To talk about the depth, so this depth where the channels, where the electrons are situated, it is only 5 to 10 angstroms. So it makes sense to say that when you create the entire device stack, so you will have a source and a drain electrode which will be ohmic in nature, and if you are able to make these contacts roughly equal to the depth of this gallium nitride plus algan plus aluminum nitride, you will be able to make an electrical connectivity with respect to the two-depth channel. Then you have a gallium nitride layer, which is basically to prevent any leakage that can go from gate directly to the channel. And then finally, you have a passivation to passivate any unwanted surface state on top of the gallium nitride layer. So this is the general architecture of the gallium nitride HIMT, which we are discussing on silicon carbide. So uh, as we have discussed right now, so just by adding an algan and GaN layer together, and because of the surface states, all the electrons will come and sit over here and form the channel. So that means the high electron mobility transistors inherently are normally on devices. And the reason why we are calling them as high electron mobility transistors is that when these electrons sit at this interface, they are free to move between source and drain. They cannot move into the bulk of the gallium nitride. And since there is no doping, so the carrier mobility will not be affected and they can theoretically achieve their maximum mobilities. So that is why this transistor comes out to be known as a high electron mobility transistor. So discussing all these advantages, right from the intrinsic properties to the figure of merit and the different kind of stacks and how the channel formation takes place, we still find that the gallium nitride has not been used to its fullest potential. And now that happens because of several reliability issues. And to talk about it, most prominent thing that comes into the picture is called as the hot electron effects. So the hot electron effect is nothing but the deterioration in the on-state current, the transconductance, the shift in the threshold voltage, and that happens primarily because of the high electric fields. So when the peak electric field at the gate edge increases, so there will be localized channel temperature that will increase, right? So when the channel temperature increase in a localized spot, what will happen? The phonon scattering will increase. So if the phonon scattering increases, the carrier mobility will degrade. When the carrier mobility degrades, it will loop back and deteriorate your on-state current. So if the on-state current is reduced, then you will not be able to extract the maximum power out of the device that you were interested in. As a solution, you have different ideas. So you play around with the electric field. Specifically, what you can do is you can shift the gate towards the source. That will give you ample distance between the drain distance, so the electric field have a more wider distance to be modulated across. But that will increase the resistance and therefore the transconductance, which roughly I would like to call as the gain will get affected. Then you have field plate architectures, which can again suppress the peak electric field, but the issue is that again, so it will increase the gate capacitance. So when the gate capacitance increases, so the RF performance of the device gets affected. Then you have something called as the gate engineering techniques by using novel gate architecture, such as the pi gate architecture, which I'll be focusing on after a few slides. So this modifies the electric field in a way so that the hot electron reliability of the device is improved, thereby improving the hot electron reliability and of course the high power applications for the device. Apart from that, since the gallium nitride as a material is not as matured as a silicon-based technology, so there are some trap-related issues. So because of the trap-related issues, the current that you predict from the normal DC characteristics is not the current that you get when that device is, let's say, subjected, or when that device is employed for any RF application, for example, or even for a power amplifier or a LNA. So as a result, the current so we call this as current collapse, and your output power grid compressed. So to deal with that, you have again different techniques. So you can go for different kind of passivations. You have a field plate technology like we have discussed. Then the gate engineering techniques are also there. Or there's another technique which is called as a high resistor gallium nitride buffer. So the idea here is to intentionally compromise the crystal quality, thereby making the layer resistive so that there's no leakage path that can be adopted from the bulk of the gallium nitride. But of course, this design is really critical and it is very difficult because any miscalculations can significantly increase the trapping instead of reducing it. Then people have studied back barrier techniques by eliminating the doped or the highly resistive gallium nitride buffer altogether, so where the back barrier can improve the 2-day confinement. So these are the two things that I will be focusing on throughout my presentation. Now, the different techniques that we have discussed, so people have explored that in order to improve the performance quality of their transistors. But still, there's always a demand for scaling up the device, scaling up the frequency where the device can operate. And for the gallium nitride hint, as it turns out, the idea is to have the device operate to be able to operate at higher frequency at the same time to give a higher output power. So what you need a high frequency, and at the same time you want your technology nodes to be scaled down. So if you ask anybody how to scale up the device performance or how to scale up how to make the devices compatible to a high frequency, they will say, okay, you go ahead and scale down the technology nodes. But when you do that, of course, the short channel effects will come into the picture, and that is going to limit the applicability of your devices for high voltage operations. Then we switch to something called as the indium hymns. So in that band engineering diagram, if you will observe, so the indium in NaLN specifically, it sits on top of the gallium nitride. So that means the NaLN is lattice matched to the gallium nitride. So even though the piezoelectric coefficient is not there, the compound stability is very high. And at the same time, it has been observed that the polarization in terms of the NaLN is so high that it can give you sheet carrier density twice compared to what we were discussing right now. But now the issue is when you have so much electron carriers at your channel, you need a better electrostatic control to be able to modulate that channel. So what you will have to do is you will have to reduce the distance from the gate towards the channel, which is where what you will do is you will reduce the thickness of that barrier. Now, when you do that, of course, what will happen if you're reducing the thickness will increase the gate leakage current, then of course your efficiency of the whole efficiency of, let's say, of the power amplifier will get affected. Then you have some considerations like we discussed, make the buffer resistive intentionally, but again, it can lead to current collapse. Or the best case alternative in this case is using the back barrier techniques, which we'll be focusing on in my next slide. So moving on to work that we had that we had done. So we focused. So we fabricated the indium aluminum nitride HIM. So this fabrication, of course, was done with the help of hello. Am I audible? Hello. Hello. Am I audible? Can somebody confirm?
Hello.
Hello.
Am I audible?
Yes, ma'am. Yes, sir. Yes.
Yes, so there were some connectivity issues. I'll share the screen again just to say. Look, I hope the screen is visible right now.
Visible, sir.
Uh, yeah, could you please tell me where the connection went off so I can repeat those things again? So I think this was okay. I got disconnected right here, I think. All right. So I was talking about the NALNM. So this particular device architecture was fabricated at SSPL, and this features a T-gate architecture right here, and it features a novel ohmic contact recipe that was again developed at SSPL. So I'll be talking about it briefly towards the end of my slides. So this figure right here, it depicts the two gate electrodes, or to be technically accurate, this is called as the gate fingers. You have a source pad here, you have a drain pad here, and then when we characterized it, we observed that the maximum drain current that this device exhibited was about 1.5 amperes per mm. So initially, what we did was we made a TCAT model out of this, and the reason for switching to a TCAT model was simple because when you're when the cost or the investment that is involved in fabricating such transistors is very high, so we wanted to be doubly sure about the optimization that we are doing. And when we analyzed the offset characteristic, we observed that these devices had a premature breakdown at only 17.5 volt. So that goes against everything that we were discussing about the devices being used for high power applications. So to discuss what actually was happening, we look at the electric field contours that were saved at the breakdown condition. So the one of the reasons because of one of the reason of this premature breakdown was the decrowding of the electric field at this region. So this is the peak electric field at the gate edge that happens because if you apply a simple physics, negative gradient of voltage gives you the electric field. So that is one of the reasons deteriorating the DC performance of this device, despite having a very high current, despite having a very good on-to-off ratio and transconductance. So next, what we did was we wanted to investigate what actually was happening. So we recorded the transfer characteristics at different applied bias, and what we observed was there was a roll off in the threshold voltage as we kept on increasing the drain bias. So this points us to believe that this was happening because of short channel effects. But when we did some literature survey, we found out that the aspect ratio, which is defined in terms of the gate length to the barrier, if that value is above 15, you'll be able to avoid the short channel effects. For the device architecture that we are considering, this aspect ratio is 25. So of course, this cannot be linked to the short channel effects. So what eventually we found out was that at higher drain bias, the confining potential of the two deck was getting disrupted. So what that means is, even though the gate was being put to a negative value to deplete the channel right here at this section, at higher drain bias, the electrons were taking an alternative path from the bulk of the gallium nitride to create some parasitic leakage paths. So accordingly, the gate had to be put to a much more negative value, as you can see right here, in order to extend the depletion region to the bulk of the gallium nitride, so that any other parasitic leakage paths could be removed. So the combination of these electric fields and those leakage paths from the bulk of the gallium nitride was what was deteriorating this offset breakdown characteristics. So if the offset breakdown is low, you'll have a less room for applying that drain bias for any amplifier applications. So we wanted to optimize this, which is where we thought of two ideas. So one was in form of the gate engineering and one was in form of the epi layer engineering. So this just summarizes the four different cases that we have. The main thing to focus here is the advantages that we are getting with the Pygate architecture. So with the Pygate architecture, you are basically reducing the electric fields, specifically at the gate edge. So when you reduce the electric field, what will happen? So this is just a depiction of the band diagrams when you apply a bias. So as you keep on applying the bias, this band bending will become more and more steep. So that will promote the follow Nadheim tunneling and even the pooled Frenkel tunneling. So the leakage current will increase significantly. So with the Pygate architecture, this band bending gets a bit relieved, as a result of which the gate leakage component due to the follow Nadheim and the pooled Frenkel will reduce, and as a result of which the gate current will come down. So that was the first idea. The second idea was we wanted to reduce the leakage paths from the bulk. So if you see the black line here, that was the original device that we had. So when we add the back barrier, specifically talking about the algan back barrier, you can see how the conduction band increases. So, by looking at this diagram, you can see that this will force the carriers electrons to stay right here instead of adopting any bulk gauge leakage path that you are getting in the gallium nitride original device architecture. Now that is also evident from this electron concentration contours, as you can see right here. So this black curve is the original case. You can see that the electrons can still access bulk or much of the bulk region of the gallium nitride channel. But in the second case, when we add the back barrier, they have been restricted to a smaller area with respect to the channel that we are talking about at this section right here. To see what happens to the DC characteristics, you see here. So just by converting the simple to a Pygate engineering, you can see that the subthreshold leakage current has reduced. And at the same time, there's an improvement in the gate leakage current by over a decade. By over one order. This gets further improved when you switch to a back barrier architecture. As you can see right here, the switching becomes also steeper, and at the same time, with the back barrier and a Pygate architecture, which is reflected here in the green color, you can see that you have reduced the gate leakage current from 10 to the power -4 all the way to 10 to the power -7. So that is the kind of advantage that we are looking at by combining both. And then focusing on the roll-off. So this was the original case. Just by adding the Pygate architecture, or I can say just by reducing the peak electric field, you can see that it was a little bit improved. Then when we added the back barrier concept along and coupled it with the Pygate architecture, you can see that the roll-off on the threshold voltage has been contained to a wider applied drain bias voltages. Now to discuss about what is happening to the DC characteristics, the graph on the left hand side, this shows the offset breakdown, which was the original case, about 17.5 volt. Just by reducing the peak electric field of the pi gate architecture, you see that it has boosted by about 50%. With the back barrier architecture, you reduce the parasitic leakage paths, and then just when you add the pi gate architecture on top of it, so this green graph is the best case scenario that we have. So we have increased the breakdown voltage all the way from 17.5 to 50 volt. At the same time, if you focus here, the Johnson's figure of merit, so the Johnson's figure of merit for this optimized architecture stands at 2.4, which is like we had discussed. So these materials can be tuned for a high JFM. So that means they can be either tuned for high voltage or high frequency applications. Now, before we discuss and before we go ahead and say, okay, this is the optimized architecture, we really need to evaluate how this device will operate when you're subjecting it to any physical conditions where the transistors are potentially likely to be operated in. So, which is where we discuss something called as the pulsed characteristics. So this is nothing. This is simply a series of stress and measurement cycles. So what you do is you deliberately stress the devices. And in this case, we are stressing it at a gate voltage of -5 and a drain voltage of 8. So this is the pinch off condition where the channel has been depleted, and we are deliberately applying a higher drain bias, forcing the carriers to adopt any bulk leakage path, and we wanted to see how this affects the overall characteristics of the device. And then the measurement window was just a few nanoseconds. As you can see here, this graph here, you can see that the black lines here correspond to the normal DC characteristics that you do, and this red graph is the pulsed characteristics. So this reduction in current is basically what we refer to as the current collapse that I had initially discussed. So after doing that, we wanted to see what actually was happening. So this is for the original architecture. So we did something called as the pulsed transfer characteristics, and we observed that as you kept on reducing the measurement window from, let's say, 500 to 200 to 50 nanoseconds, you see the shift in the threshold voltage with respect to the original curve was a bit significant. Now this is very important. This becomes really significant because let's say when you design any power amplifier, you have some Q points that are fixed. But if the Q point changes dynamically during the operation, that will affect the overall performance of the entire system. So observing how this changes. So when we switch to a pi gate architecture, you can see how the spread in the threshold voltage has been reduced. And to quantify it, so for the original structure, the shift was about 0.9 volt, and with the pi gate architecture, we are having about 0.4 volt. And when you add back barrier on top of this, you can see with the pi gate architecture, again, the best case scenario, you have reduced that shift in threshold voltage to as low as 74 millivolt. So moving on to the last signal analysis. So here we do something called as a load pull analysis, just to see how well the device can operate for a large signal analysis. So here we are biasing the devices in class AB operation, driven by a frequency of 12 gigahertz. So this is just a comparison of the conventional architecture with the pi gate architecture. So first and foremost, you can see there's a more modest trade-off to the power gain that you are getting. At the same time, the advantage is in terms of the linearity, as you can see right here, the slope of this graph right here, that is the output power as a function of input power. And that is also reflected from this graph right here, which is called as the third order intercept. So a higher third order intercept, specifically at the saturation region, it basically evinces the fact that this particular device architecture has a better linearity compared to its original counterpart. And by linearity, I basically mean that it is adding a lower degree of unwanted harmonics when it is amplifying, when it is being used for any amplification process. And since we were able to scale up the off-state breakdown voltage, so this graph here shows the output power as a function of the drain bias. So this is the original device, which had output power of about 1.6 watt per mm. With the pi gate architecture, we scaled it to a little above 4 watt per mm. For the green architecture, that is the best case scenario. You can scale up the device powers from almost about 1.2 watt per mm to all the way to 5.2 watt per mm, while still retaining a good third order intercept and a good linearity. So To summarize, so this slide actually summarizes all the results in the later half of my slides with respect to how the Pygate architecture is giving you a better hot electron reliability, reducing the current collapse, and how the inalienable HEMS is basically opening up avenues for high frequency applications. But to just to give you a perspective of the gallium nitride versus silicon-based electronics. So, of course, the gallium nitride-based electronics is dominating the silicon-based electronics, but the silicon is here to stay. And the reason why I say is that the novel ohmic contact recipe that I was talking about, so that ohmicity in gallium nitride-based HEMS is also ensured by silicon as dopants. And on the other hand, if you see the applicability of the gallium nitride, so the lighting in your classrooms, the power chargers that you're using for your laptops or your phones, or they all are essentially made from gallium nitride or silicon carbide based technologies. And since if you target defense or space applications, which is where the gallium nitride on silicon carbide based architectures are generally preferred, and the reason is simple: the lattice mismatch of the silicon carbide with gallium nitride is around 3%. So for any defense applications, you would want to keep the defect density at a minimal point. But when you go for gallium nitride on silicon kind of architecture, the lattice mismatch is around 17%. So that introduces high density of dislocation defects. Now, those kind of dislocation defects are not so good for any RF application that concerns the defense application. So which is where the research is going on. But those kind of transistors are still used for enhancement mode operations, which are of interest to the switching to high power switching applications of interest to, let's say, the EV or the EV industry. So and the reason behind keeping silicon is simple. So when we talk about the investment, so the gallium nitride on silicon carbide, if you go out, let's talk about the silicon. So if you go out and buy a high quality silicon wafers, so you'll get a 6-inch or 8-inch wafer in around 20,000 to 50,000 rupees. But talking about the gallium nitride on silicon carbide, for a 4-inch wafer, it costs you anywhere between 7 to 10 lakh rupees. So that is the kind of investment we are talking about. So the gallium nitride on silicon gives you an advantage that it can be integrated with the already existing silicon-based electronics for a multitude of applications. And for the acknowledgements, I would like to thank my collaborations from DRDO, Deen Dayal Upadhyay College, and the present workplace, that is Faculty of Technology, University of Delhi. These are some of the references, and thank you. That's it from my side, and I'll be happy to take any questions with you.
Thank you, sir. So for this wonderful session, can you hear me, sir?
Yes, I can hear
Okay.
you.
So actually, I'm not into this field. I'm from microwave field, and there I am working on millimeter wave and terahertz frequency range.
Yes.
And for that, I'm designing LNA and subharmonic mixer, those kind of things. So what I came across, instead of using that device level thing, I am using like discrete HEMT component, right? So
Yes, yes.
their HEMT component for low noise amplifier, it is like a suitable candidate for that. But nowadays, gallium nitride and as you told, like silicon carbide. But I have utilized gallium arsenide only. So why we should go for gallium nitride and silicon carbide, sir? Can you just explain this?
Yes. So for explaining that, I'll go back to my initial slides. Let me go back just a little bit. Yeah, this. So like I said, of course. So when we want the devices to be operated at high voltage, so when the operation when the only application that we have in mind is to apply maximum voltage, and let's say to have the operation domain in kilovolt regime, that is where the gallium nitride and silicon carbide will come into the picture. That is the only domain area. But if you say that, okay, I want a high frequency operation, like you mentioned about the operation in let's say
Millimeter. Yeah,
Terahertz
terahertz also. Okay.
So for
Sir.
yes. So for terahertz domain, the gallium arsenide is the only material that can give you very high mobility. And apart from that, you also have other alternatives such as the indium phosphide hands. So pseudomorphic hands, you must have come across the name. So
Yeah,
all these materials,
PHEMT we are
yes,
using.
yes. So
Yes, sir.
those are based on either the gallium arsenide or either on the indium phosphide based hands. They have a high carrier mobility, which will enable you to target that frequency range, but that will be at a lower voltage, as you can see right here. So if the only objective is to have operation at high frequency without worrying too much about the voltage levels, then gallium arsenide is your choice. But if you want to have a trade-off, you want to have a high voltage operation as well as a decently high frequency operation, then gallium nitride is where you go. So
What
even for
about
gallium,
the noise figure, sir? Noise figure will be decent for this component, gallium
yes.
nitride and.
Ye-
Okay.
Yes, gallium nitride is being used for LNA applications as well. So just to give an information. So this I think information must have everyone must have come across. So when when our government had a Rafale deal with France, so they initially denied giving this gallium nitride based technology. So this has been developed by DRDO, SSPL. And so what they're doing is, so there's a single chip in which both the power amplifiers, the LNA and the switch, all these things are being integrated into a single chip. So the LNA is also there, the high power amplifier is also there, and switch is also there, and they're working perfectly for all the ASA radars and all the military applications. So again, if the voltage is a constraint, then you will have to go to gallium arsenide and indium phosphide for low voltage applications. But if you want a high power, or in other words, if you want, let's say, a high gain, because for LNA applications you are looking at gain mostly, right? So there gallium nitride will come into the picture.
Okay. Sir, one more query I am having, sir.
Yeah, sure.
Actually, I am designing like hybrid kind of IC, like where I am buying some gallium arsenide PHEMT and then I am soldering that thing. But if
Yeah.
I want to do in like complete IC form, okay.
Hmm.
So like how can we proceed further for that? Because I am not into that VLSI domain. So, like,
So
if Foundry will give me that GAN or GIS file,
yeah.
like,
Yes. So talking about tools, there are 3 tools that industry people use for designing this. So I think Keysight ADS, then
yeah,
AWR,
Keysight
so
I am
all those
using,
things
sir.
are right.
Keysight I am
Yes.
using for that.
Yes.
But the
Yes.
problem
So
is, yeah, because they have some standard library there, like
yes.
they,
Yes.
yeah.
Yes. So
So,
to get the library, so you have to sign an NDA. So for one company that used to give was Cree. So that
yeah, yeah.
now the name has changed to Maycom. So they used to give gallium nitride based PDKs.
MACOM, you are saying, sir? MACOM. MACOM.
Macom, yes, yes.
Okay.
And
Okay.
and apart from that, if you're really interested in, let's say, the P hems, the pseudomorphic hems, which is where there are some outdated libraries, of course, that is being given by HP. But UMC is one of the foundries. But in any case, any foundry that you come across, you'll have to sign an NDA. They will give you the PDKs, and those PDKs will come with the layer geometry and all the information, so that whenever you go for any schematic, you design any schematic, that is fine. So that you can do with ADS, no issues. But the main thing is, you go back to your layout and you check whether your design is working or not. So if you do not have the layout information associated with your PDK, you will not be able to complete the whole process, which is where the NDA will come into the picture. So whenever you sign an NDA, they will give you the entire PDK, which has the layout information. So all the design that you will do, it will be translated into a layout. And from that layout, you will do something called as a co-simulation, and then it will be an iterative procedure.
So you
So
told NDA, na,
NDA,
sir?
yes. So it is a non-disclosure agreement where you will have to say that you will not disclose or you will not attempt to reverse engineer what they are doing, or to encode it. I mean, to decode what model they are using. So they will just simply provide you the large signal models so that you can use it for your applications.
So what I had done for my design, like let's say if I want to use ATF 55143.
Yes.
Okay. So I had given just a spice model for that, and parasitic resistor and capacitance value was considered
Right.
in that model. So I have done. And till now, I have not tasted whether it is working fine or not, because that 55143 I was trying to purchase, but it is not
It is
available.
outdated. Yes, it is obsolete.
Yes, sir. Yes, it is. Yes. So, I was thinking if I can make my own device and then I can integrate, but I am stucking somewhere. That's why I'm asking you, sir.
So
But
the
yeah, you have answered it very well, sir. So thank you for
yeah.
answering my question. Okay, sir. In your future, if I will connect, if I would like to connect with you, I can have a number from Chandrakant, sir.
Right. Yeah,
Chandrakant.
sure, of course. Of course.
Oh, sorry. Thank you, sir.
Right. Any other question?
Thank you very much, sir, for your enlightening and informative talk on the dominance of GaN and gallium nitride based devices. Your presentation provided valuable insights into the significance of gallium nitride technology and its growing role in high performance electronic and communication systems. We truly appreciate your time, expertise, and the knowledge you have shared with us today. Thank you, sir. Thank you so much.
Thanks a lot. Thanks a lot. I'll sign out.
Okay. Now, we will now break for tea. The next technical session will resume at 12:15 p.m. Kindly reassemble on time.
Thank you, sir. Thank you, Kusman sir, for accepting our invitation. हाँ एक मिनट बात कर रहे हैं मैं सीधे काट रहा हूँ।
Welcome back, everyone. We now move on to our next technical session. It is my pleasure to invite Dr. Chaya Dalila, who is an associate professor in Department of Electronics and Communication, JSS University, to kindly introduce our distinguished speaker for this session. Over to you, ma'am.
Yeah, good morning to you all. It's my privilege to introduce Dr. Ravindra Jha. Welcome you, sir. Dr. Ravindra Jha is an assistant professor in the Department of Electronics and Electrical Engineering at IIT Guwahati. And he is associated with the interdisciplinary programs in health science, sustainability, and design. His research focuses on semiconductor devices beyond silicon electronics. He is a recipient of prestigious fellowships, including the D.S. Kothari and SCRB National Postdoctoral Fellowships.
एक मिनट ना रवि वो लीविंग ज्वाइन
Okay. Dr. Jha has authored over 100 peer-reviewed publications and delivered more than 100 invited talks at national and international forums, including leading IEEE sensor conferences. He is a senior member of IEEE, a governing council member of IEEES, and the founding chair of the IEEE Sensors Council, Kolkata section, and Guwahati subsection chapter. Welcome you, sir. He is just about to join. We wait for a few minutes.
Sir will be joining very soon.
Hello, Chandrasekhar ji, can you hear me? Just 1 second. I'm not able to hear you. Just give me a minute.
You are audible, sir. Clearly audible.
Good afternoon to you all. Welcome you, sir. I welcome Dr. Ravin Jha, sir, to as an expert. I brief the profile of the sir. Dr. Ravin Jha is an assistant professor in the Department of Electronics and Electrical Engineering at IIT Guwahati and is associated with interdisciplinary programs in health science, sustainability, and design. His research focuses on semiconductor devices beyond silicon electronics. He is a recipient of prestigious fellowships, including the D.S. Kothari and SCRB National Postdoctoral Fellowships. Dr. Jha has authored over 100 peer-reviewed publications and delivered more than 100 invited talks at national and international forums, including leading IEEE sensor conferences. He is a senior member of IEEE, a governing council member of IEEES, and the founding chair of the IEEE Sensors Council, Kolkata section and Guwahati subsection chapter. Welcome you, sir, once again. The title of talk of sir is Beyond Silicon Electronics, 2D Materials for the Next Generation of Semiconductor Devices. Over to you, sir.
Thank you, ma'am. I hope that you are able to see my presentation. Is it visible?
Yes, sir.
Okay.
Visible, sir.
Acha, you can hear me also, right? Okay.
Yes, sir.
Yeah. So then I will start.
Yes, sir. You can start, sir.
Okay, okay. So yeah, so thank you, JSS team, HOD and Professor Chandra Shankar. I think this is my third interaction with JSS, and I think second with the JSS Noida. JSS Mysore
Yes, sir.
also.
Sure, sir.
Yeah. So yeah, thank you. Actually, what happened? Admissions are going on right now, orientation and other things. So I got 2-3 minutes delayed. I'm really sorry for that. Yeah. So my presentation will be on a topic which some of us, if even if we are working in the domain, are may not be, familiar with. So I have kept it in very kind of layman language. Particularly if you are working in design and you are not from the semiconductor device side, you may find it sometime, you know, what you say, uh, you may not be able to accept few of the things. So maybe that is fine. I mean, you don't have to uh, understand each and everything, but I hope that at the end you will understand the gist of this talk, particularly what we are doing in 2D material. Like, I have already invested about a decade of my life doing this 2D material, and believing that the future is future electronics will be built upon the 2D material. Of course, no issue with silicon, but the thing is that there are some requirement from the device perspective which are not being able to fulfilled by silicon, on which the complete industry is relying upon. So maybe integration. So it's not key. We are moving to another domain of devices. We are sticking to silicon only, but what we are trying to understand in this talk, that how the next generation 2D materials can be integrated with the current generation silicon electronics. No technology, can emerge as individual technology. It is built upon something which is already existing. So a lot of interest is in integrating the 2D material based devices with the silicon electronics. So beyond silicon electronics in this title do not mean that I'm talking something which is actually leaving besides the silicon. Actually, the talk is of inclusion of 2D material in the current silicon technology. With this, let me start. This is our IIT Guwahati beautiful campus. Some of you might have not visited. Some of you were passing Guwahati might have definitely come here. So this is a kind of paradise on the earth, not only to you know uh, spend quality time. You can also do some good research over here. Everything is very supportive, including the admin and the ambient. And the state, of course, you might be knowing that Assam is pushing a lot of things in semiconductor. Already a 27,000 crore investment. I think you might be knowing one of your alumni is also heavily involved. Um, um, in Tata Electronics plant that is coming nearby in Jagi Road, just 1 hour away from our campus. All right. So this my research domain is on 2D material based electronic devices, and we mostly use it for sensing applications. But then, of course, that is the post device applications. You can use it for whatever application you get, but then you have to be a hardcore device engineer. So we also intend to do packaging of our in-house developed devices, and we use a lot of fabrication tools like using lithography, including photo and electron beam lithography, and then maskless lithography. Recently we procured laser based direct write lithography. Okay, so we do a lot of patterning as well. um, then of course data analysis, and also of course today we are not going to discuss them, but we will focus only on the 2D material part. Okay, so then with this introduction, let me start with the what we are going to discuss today, which is the beyond silicon. As I have already mentioned that beyond silicon electronics actually refers to the electronic devices and systems which employ materials and architectures other than the bulk silicon to sustain the progress which is beyond the limitation of conventional CMOS scaling. And all of us know that the conventional CMOS scaling is limited by the Moore's law, right? So Moore's law, if you are not aware or if you are joining late, 65, Gordon Moore observed that the number of transistors integrated on a chip doubles approximately every 2 years, while the cost per transistor decreases. Okay, so this do not only bothered the device engineers, but also it bothered the future design engineers also. Okay, because if you can, I mean, sometime it is exciting, but then sometime you have to also think that how you are going to accommodate all of them. Okay, but of course this is an empirical formula. There is no I mean, Moore's might have done a lot of mathematical calculation, but for us it is a empirical formula. Okay, and of course it can fail as well, but till now it has been working well. Okay, so this observation of Moore has driven the semiconductor industry over 5 decades since initial ICs were discovered by enabling the continuous improvement in the computing performance, efficiency, and the device miniaturization. Since I'm a device engineer, I look from a device miniaturization point of view. Then design people, they look from computing performances and efficiency performances. Okay, so initially, Moore's law was sustaining primarily through geometry scaling of the MOS devices, and then reducing the transistor dimensions increase the packing density, which improved the switching speed, but then it also lowered the power consumption. So that is what we actually require in ideal case for any from any device or any chip. Okay. However, as technology progressed from micrometer to nanometer, which of course we all are aware, because whenever we buy a mobile phone or a laptop, we see that at what technology node it has been fabricated. And even it is say little bit of deviation, we prefer the other one, which has a better dimensionality. Okay, so then there are different advances in lithography. Okay, earlier it was thought that the country where fabs are available are the someone which is at the forefront of semiconductor industry. But then these technologies are very much lithography driven, and now the companies are particularly with the inception of this deep UV lithography and others, now it has been a debate that maybe you may have a fab in your country, but what lithography tool you have? Do you have expertise in deep UV, or do you have any other alternate technology for that lithography? There are only a few companies which has been pioneering that domain, and of course with that lithography system come other things, as you know that in the process you require photoresist. So for that particular lithography you require that particular photoresist. Then for that you need particular developer. Okay, then etching system. So lithography basically define your complete process. Okay, and that's how India is tapping this particular market. That okay, if I cannot tap at say 2 nanometer, let me tap at any other scale, and let's see. How these companies are going to perform. Okay, then there are advancement in the high-K dielectric materials, then strained silicon, then FinFETs came, then gate-all-around transistors came, and these technologies actually further extended the silicon CMOS technology. Okay, and now people are talking about this nanosheet and other kind of transistors. I will talk in very brief today. Okay. Now, as the transistor dimension approached to the sub 5 nanometer technology node, the conventional silicon scaling encountered several fundamental physical limitations. Okay, some of the limitations are like you might be aware of, like increased short channel effect due to insufficient gate control. Even at the undergrad level, where we are not discussing sub 5 nanometer, there also we have learned about the short channel effect in the transistors. Okay, then when you talk about this kind of scale, uh, always you will have a higher leakage current. Okay, particularly if you see the on current and leakage current, they become very comparable. Okay, and this kind of leakage current results mostly through from the quantum tunneling through the ultra thin gate dielectrics. Okay, then you have increased contact resistance and parasitic capacitance. When you are talking about channel length of the order of say 2, 3, 4 nanometer, okay, and you are talking about very low resistances, then contact resistance where you are probing your device itself is the biggest problem. Okay, particularly with the some of the materials has tendency of Fermi pinning. Okay, so that kind of problem arises, and then you have a lot of parasitic capacitance which has to be tackled. Okay, then power density and thermal management challenges always exist. Anything beyond 45 nanometer or so. Okay, and then significant process variability is there due to the atomic scale fluctuation, because that will be very prominent when you are talking about a scale of its dimension. Okay. However, these limitations indicate that simply reducing the dimension of silicon transistor is no longer sufficient to maintain the historical pace which was predicted by Moore's law. Okay, so the semiconductor industry has shifted from more Moore. Earlier, it was called, which was like continuous transistor scaling, to beyond Moore. Okay, so there are a lot of debates on it. You can find a lot of very good papers which are only developing more Moore concept and beyond Moore concepts. Okay, where performance improvements increasingly depends on new materials, novel device architectures, and the heterogeneous integration, which is talk in the town, particularly when you are trying to integrate chips from different what you say foundries. Okay, and then when you have this kind of heterogeneous integration possible, okay, your electronics is now no is not now limited to the conventional packaging and other techniques, because I mean, even with the 3D packaging and others, there were several challenges, and many of it has been sorted out by heterogeneous integration. Okay. Now, coming back to 2D materials, okay, which is our today's discussion. The 2D materials have actually emerged as one of the most promising candidate for beyond silicon electronics because their thickness is naturally limited to a single or few atomic layers. When I say single or few atomic layers, what I mean to say that let me take a pen, for example. Okay, say if I'm talking about say graphene. Okay, this yellow box that you are seeing is the only layer available. Okay, but as we know that graphene is a semi-metal, and in this channel we want a semiconductor. Okay, so just after the inception of graphene in 2004, what people does is they started looking for a similar structure material but having semiconductor property, and they came across uh, uh, a family of material which is known as transition metal dichalcogenides. I will use the word TMDs for it. Okay, in the short form. Okay. Now, when I have a TMD, as the name suggests, transition metal dichalcogenide. So I have a transition metal for, say, for example, tungsten with two atoms of chalcogen family. Say, chalcogen is the oxygen family. Say, for example, sulfur. Okay, oxygen and sulfur are from the same family. Okay, so I have this kind of structure. So sulfur, tungsten, sulfur, and if I see its monomer, it looks something like this, for example. Okay, like this. So you have, I mean, similarly, you can have this kind of structure over here. Okay, and similarly, it can extend. And say, for example, here it is tungsten. This corner is then sulfur, and then again it is tungsten, and then it is sulfur, and so on. So that's how you are seeing that only. So the structure is very clear that one transition metal is sandwiched between two uh, chalcogen atoms. Okay, so this is kind of structure. Okay, so they have, I mean, people has found that, okay, we have now a semiconducting, I mean, very interesting semiconductor materials. I will come back to it later. Okay, unlike bulk silicon, these TMDs or these 2D materials have atomically thin channels. Okay, it can form atomically thin channels which provide nearly ideal electrostatic control over the channel potential. Okay, uh, this actually significantly suppress the short channel effect even at extremely small gate lengths. Okay, and that's how it has become very popular for devices in the beyond silicon era. Okay, And I just want to brief you that there are multiple applications that has been demonstrated with this kind of material, like in the digital to analog chips. They are available. People are doing a lot of quantum. They are making a lot of quantum devices with this kind of materials. For AI chips, it has also got some attention, and of course, sensing chips are something which is many groups are also looking. Okay, so the idea is simple. You have to optimize the material, because material synthesis or fabricating this material or thin films of this material on different surface itself is a challenge. Integrating it with the silicon itself is a challenge. Okay, if you remember, the silicon electronics has evolved because it was not like silicon is abundant or it can be made from sand. That's why it has emerged. Actually, it was the SiSiO2 silicon oxide neat junctions. Okay, or you can say that I do not if say I want to have a silicon oxide junction, I do not have to primarily deposit silicon oxide. What I can do is I can also do the thermal growth of silicon oxide with a very neat interface. Of course, it will have much better, even it is amorphous, it will have a very neat interface at this. Okay, so depositing these 2D materials itself on different substrate, it challenging. All right. A lot of challenges are there. I will show you some work also. Okay. Then optimizing these devices and designing circuits for these devices. All right. And then integration with the current chips are some of the challenges people are trying to take. Okay. So these 2D materials have different promises to fulfill in nearly all the domains. Whatever work you are doing, okay, these materials has that tendency to solve your problem, okay, because this family has all kind of materials, like you have metals. I mean. Materials with the metallic characteristic. Okay, then you have semi metals, then you have pure semiconductors, insulators. This is a very important class of material which is required for device applications. Okay, HBN particularly has emerged as one of the important insulator. Then you have superconductors. Okay, some of the examples are shown over here. Like if you see, say, this is a VS2. I'm sorry for it is VS2. Okay, so this is TIS2. Sometimes it has confusion that TIS2 is semiconducting or semi-metallic or metallic. Okay, we have done extensive study on TIS2, and paper is in the domain in the public domain itself. Okay, then in semiconductor you have both dichalcogenides and monochalcogenides. Okay, then these of course comes under different families. Okay, you have different family of 2D materials. So I just mentioned a name of 2D class of 2D material, that is transition metal dichalcogenide, but then there is a complete class of these materials, and they are going to stay, they are not going to leave. They are going to stay for years. Okay, what is interesting in this, if you see, okay, that you can also have a single atomic material as a like for example black phosphorus or others as a single layer, that is also available. We call it homoatomic materials. Okay, um, so that is again of interest, similar to graphene, which is derived from carbon. like there are interest where people are trying to look for different materials. Like for example, borophene has been kind of derived from boron. We also do a lot of boron engineering for different applications. Okay. Then, if you see, there are multiple fundamental promises that are made by 2D materials. Okay, like again, this is not only because they are compatible with this current CMOS technology or so. They have multiple fascinating properties, including their thermal properties, their optical electrical transport properties, their electrical and say other properties, bioactivities, mechanical properties. Okay, there are n number of promises made by these 2D materials because of their multiple qualities. Okay, dimensional confinement results in emergent properties because when you are trying to so if I ask that what is a nanomaterial, usually we call that okay, anything which has dimension of 100 nanometer, 200 meter or so. But actual definition of nanomaterials are like the materials where surface properties dominate over the bulk properties. Okay, so if say for example, if I have a graphite, okay, graphite has most of its property coming from its bulk. Okay, as soon as you took the top layer, okay, now the complete surface is itself a layer. Okay, so but particularly what you are trying to do here is you have converted this bulk to simple surface. Everything will have a bulk component, but then we have to see that how surface is dominating over the bulk. Okay, or bulk is dominating over the over the surface. So like in the thin film, for example, here a thin sheet of graphene, for example, the surface is something which is dominating over the bulk. I hope that I am going very slow and you are able to understand, and I'm going at very fundamental level. Okay, so you are not having any dangling bonds, and basically it is helping you with electron transport. So for example, in only in the x and y direction, so there is no z direction movement, and you are able to confine the electron movement. So once you have that much confinement, you have better control. Okay, similar things with the optics. All right. So, as I was mentioning, different families dielectric families, then semi-metals, metals. These are just different classes, okay? But I'm not mentioning it from the property point of view. There are, materials where you can have tunable band gap. For example, take the case of TMDs, okay? TMDs, for example, say if you take a bulk MOS2 or say WS2, when I started working on this say WS2 in 2012, I found papers from 1969, 70. It's not a new material. I found those papers where these materials were used as a lubricant. Okay, the people were using it in the cycle chain or in industry. If you search, you will also find that kind of papers. Okay, but it's not a new material. Okay, but its property is what is something which has been explored very recently or has been checked recently. Okay, for example, this WS2, for example, when it is used as a lubricant in cycle chain or some say some industry where motion parts are available, moving parts are available. Okay, now this bulk WS2, for example, is a indirect band gap semiconductor. Okay, now when you thin it down, so when I say it's bulk, it means that it has thousands of layers. So these are van der Waal materials. When I say van der Waal, it immediately it should come to your mind that this is a weak physical forces. Okay, So, for example, this is, I mean, a layer of WS2. They are stacked over each other. Okay. Now, what happened that when I say weak physical forces means that the weak physical forces can be broken down. Okay, and that's how the sheets can be removed from the bulk part. Once you remove this sheet, now that electron I was talking about will have that kind of property, and now it has, and of course the monolayer of these materials are direct band gap semiconductors. So this is a same material having indirect band gap as well as a direct band gap when you peel it off or when you thin it down. All right. So these are just some of the fascinating properties. I mean, if you go on and read about these materials, you will find a lot of interesting properties. Okay, and this is a kind of terahertz and microwave applications where these materials has been explored. I mean, a lot of materials are available, thousands, I would say. Okay, so you never know that what I mean what is suitable, what can be, or what I would like to say, ki what band gap might be suitable for what fascinating property, and it may come say next day in the news. Okay, that okay, people has found this application with this 2D material. Lot of groups are working on this, and lot of work is going on this materials. Okay, so, core promise, which is of today's agenda, is the electronic structure engineering. So, these are the core promises of 2D materials. Like band gap tunability is quite possible, not only by thinning it down by reducing the layer number, but by changing the strain. Okay, so there is a new electronics which is known as twistronics, which is similar to the like spintronics was developed some years back. Okay, or I would say more than decade ago. Similarly, twistronics is something which is very close to these materials, because you have thin sheet, you can twist it and see the properties. Okay, band gap tunability is also possible through defects in this material, because defects in these materials are very special. Okay, uh, then by chemical functionalization, all this transition from direct to indirect is possible. And at atomic scale channels, you have very high on-off ratios in the transistors, and that's how these devices have very core promise for the electronic industry. Okay, this atomically thin channels give short channel immunity. They reduce your surface roughness scattering and have high mobility band gap coexistence, which is one of the key challenges that has to be solved. Okay, although if you see mobility is not that great. Okay, however, of course, by doping and other things you can improve. And as I mentioned, every day a new 2D material is coming. So a lot of engineering is going on to increase these things, and you may see all 2D material based transistors existing. Okay. Now the challenge is in the silicon scaling, as I have mentioned earlier, that you have poor gate control at short channel. Okay, and you have high leakage current, and then mobility degradation. So okay. Now this 2D, with the 2D materials, you have high control on the from the gate side. Okay, you have larger band gaps in semiconductor 2D materials, which suppress any off-stage leakage, and some 2D materials retain very high carrier mobility even at atomic thickness, and this can be further improved by having heterostructures of these materials that I will talk in a minute. Okay. Uh, you have absence of dangling bond, which minimizes the interface scattering. Okay, then monolayer channels can potentially operate at gate length much below than 5 nanometer. Okay, now Another important thing is the integration complexity with the silicon. Okay, you know that there is a new area of in photonics also. If you, some of you might be working in the photonics domain also. Silicon photonics is another area which is which is very popular, I would say. Okay, but the challenge they are facing is all silicon and silicon photonic structure, including the emitter, detector, and the propagation medium, and so on. Okay. Further, if you try to integrate it with even the compound semiconductors, you have a lot of challenge. Particularly if you are aware of epitaxy things, you might be aware that more than 9% of relaxation is not there on one atom to another atom, and then you use sacrificial layers and other kind of provision you use, and then again you compromise with the electronic properties. Okay, with these materials, what happened that they are van der Waals materials. So this van der Waals stacking enables the heterogeneous integration without any lattice mismatching. Okay, means that, say if you want to grow, for example, or if you want to deposit, say the WS2 on top of another material MOS2, you do not have to actually look into the lattice parameters of the material, because they are not going to stand over here. They have a physical force between them, so you have to more worry about the van der Waals stacking rather than the what you say epitaxy, okay, or the lattice mismatch. Okay, so what I have shown over here is one example of making say a hamburger where you have multiple things. I'm sorry if if these examples do not go well, but the idea is to show you that say if you want to stack all these things, or if you want to change the sequences, doesn't matter, of course. But if you will not be in trouble while growing one or on top of another, but if you change its positions, of course you will have altogether different properties. So all kind of band alignment, including type 1, 2, and 3 heterojunction is possible. Okay. In the optoelectronic side, I would say the strong light matter interaction and large exciton binding energies is something of very interesting, and the people has been looking for this materials for flexible and transparent optoelectronic, particularly for the integration of photo detectors, LEDs, and solar cells on different. Okay. Then you have mechanical and flexible promises also, because you know that the next gen electronics are not only confining uh, the transistors. Okay, they are also bringing it on different platforms, particularly with the inception of this e-tattoo, wearable devices, smart phones, I mean, smart tattoos and all. Particularly, if you see, I think Samsung day before yesterday only launched a foldable phone. Okay, and again, you may find later on some curved phones, some say conformal coatings on your textile, on your t-shirts. Okay, so on. Okay, these places not only require flexible electronics, but also your materials must have a mechanical strength as well. Okay, this some of these TMDs and other materials have very high Young's modulus and have extreme bendability. Okay, so I know several groups which are only focusing on flexible devices based on these materials. Okay, so you have a lot of opportunity from that point of view also. Okay, so I'm talking about transition metal dichalcogenide continuously, but this is what I actually mean. So M here is the transition metal and X is the chalcogen. So not only sulfur, you have selenium and tellurium also. Okay. Then this is our paper where we with a big group we tried to use it for large area. I mean, what is the challenge with these materials is to grow these materials on large area. Usually, you have a few nanometer thick sheet for at certain distance. Okay, say 1 micron sheet you can get, or say 500 nanometer sheet you get, or 200 nanometer sheet get. But industry is not interested in this. So what we want is to grow it over large wafers. Okay, and in this work where I have shown the cutout of the paper, you can also have a look on this. This was published in IOP 2D materials, where Lynn had shown that uh, large area growth of MOS2 is also possible in a big ALD chamber around 200 dia. Okay, which has a capability of integrating at the back end of the line functionality. Okay, so at low temperature, growth of these materials were challenging, but we could achieve that, and still we are working to bring down the temperature even below that. Okay, so these are some of the results that you can see. Like for example, these are some small pieces that was kept in the ALD chamber. Okay, you can see that uh, few layers starting from say 1.2 nanometers. Usually its thickness is 0.7 nanometer, but then you have to take the substrate effect also. So maybe from monolayer, then bilayer, then few layers, and till 10 nanometer we have demonstrated. And of course, this again was utilized for some device applications. Okay, so growth of these materials are very important, and low temperature, particularly the temperature compatible, I mean CMOS compatible temperatures are something which is growth of these materials is very much required. We have tried to answer some, but then a lot of opportunities still there. Okay. Um, by other routes also, like for example, this we have shown, you can see that this transparent monolayer of WS2 lying over here, and we have broken it by some electromechanical ways, and still you can see that the structure is intact, the atomic structure is intact, and nicely you can figure out from the lattice fringe also that it has not oxidized, or its properties are intact. Okay. Recently, one of our collaborator, they have we have together have done some work on TISC2, which is again emerging TMD, and again having a lot of interesting properties, and we have used a CVD method for this. Okay, so I would conclude with a line that Moore's law is slowing down as transistors dimension approaches the atomic scale. Traditional silicon scaling is encountering fundamental physical and technology limitations, and it has actually reached to its practical limits. Okay, the 2D materials offer a promising route towards beyond silicon electronics, particularly their atomically thin channels provide excellent electrostatic control, enabling low power, high performance transistors suitable not only transistors but electronics suitable for future technology nodes. These 2D materials enable a broad spectrum of next generation devices beyond the logic transistors. They hold all promises in flexible electronics, for neuromorphic computing, sensors, quantum technologies, and so on. Scalable growth and integration remain major challenge. Achieving a wafer scale uniform defect-free synthesis, or I would say controlled defect synthesis with precision thickness control, low resistance contacts, controlled doping, and seamless CMOS compatible integration. If all these things can be achieved, it would be very nice for the 2D community as well as overall the research community. All this is essential for translating laboratory scale demonstration into commercial semiconductor technologies. And our country is also behind all these innovations. Okay. Uh, some of the courses where I sometimes give some example of 2D materials based sensors and measurement systems are on NPTEL platforms. Okay, I'm thankful to all my students who are doing amazing work in whatever domain they are working or whatever problem they are solving. Okay, I'm also thankful to all my funding agencies and of course to my institute, ITG, which has taken care of me like its own child. Thank you.
Thank you, sir, for your wonderful session. I have one question. Am I
Yes,
audible?
yes, sir. Yeah, you are
Uh,
right.
Sir, in EDA tools, generally, these are very good technology and very good research we have seen. But for EDA tools, because I'm working in the analog domain, so for designing the different type of circuitry, we are using the normal transistor like BJT or MOSFET transistor for there. But the transistor based on these materials are generally not found in the EDA tools. So, why these type of lack in the gap or lack in the industry you can see? Or maybe maybe I wrong because as per I know what work I am doing or what I have listened from the other person. Why these type of implementation, material implementation, not for that transistor or that in the which should be available in the EDA tools.
Chandrashekhar I agree, completely agree with you that these the in the circuit design you may not be able to find EDA tools for this kind of materials. Particularly, I think that this is emerging and still people might have not maybe Mighty has lot of this C2 chip program or something where people develop EDA tools. Maybe soon, because see, to develop these EDA tools, all these people has to come together, right? The design engineers, device engineers, then power engineers, or many people come together, and I think still that kind of forum has not been built so that these EDA tools have that kind of capability. Uh, Recently, few companies have been trying to make not exactly, they might have not got much success, but trying to integrate from the CAD point of view, um, integrating device and then quantum phenomena, because all these materials will immediately show quantum phenomena. So until you bring all these things together, a good EDA tool for this to integrate these materials will not be available. But I hope that within 1 or 2 years you will definitely find from our country also, not only from abroad, but you will find. Yeah.
Thank you, sir, for giving this very genuine answer, because many people have the doubts because very good research, a very good research in the impact journals, we found the material waste. But to come this in the actual domain, this I think what you said, it will require some time. And we will wait for this time because also once this material based component, this highly research based material will come into the EDA perspective, we will also able to get the better results, better power consumption, better
Yes.
frequency term. Many
Yes.
aspects are there. Results or devices for our domain in that above.
Yeah. Meanwhile, also I will also look if I get any update on any EDA tool, I will keep you posted.
Thanks.
Yeah.
Participants, any other question? This is a very good session, very wonderful session. I learned a lot of things. From the
Thanks a
participant
lot.
side, any question from you? Okay, I think there is no question. So we will have one another panel discussion session, and Dr. Ravindra Jha will also be with us in that session, and that will start from 3:15. Now, I request to Acharnan, please conclude the session.
Thank you, sir. We shall now break for lunch. The afternoon session will commence promptly at 2:15 p.m. Thank you.
Thank you, Ravi sir, for joining with us. I'm highly thankful to
Thank
you
you.
for.
Thank you, sir. I will take a leave now. Thank you.
Thanks. Sir. We will join now 2:15 for the another session. So this is now announced for the lunch time. Thank you very much.
Hello, am I audible?
Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I audible?
Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design.
हाँ चल मैम दो जगह से ओपन है एक साथ टू प्लेस है
Hello, am I
Sir, you are audible. There is some technical issue. We are just.
am I audible?
Yes, sir, you are audible, sir. Yes, sir, you are audible, but your voice is going to echo.
Welcome back, everyone. We now move on to another exciting technical session focusing on Welcome back, everyone. We now move on to another exciting technical session focusing on emerging trends in VLSI design and intelligent computing. It is my pleasure to invite Dr. Shankar to kindly introduce our distinguished speaker for this session. Over to you, sir.
Thank you, Achal. Good afternoon, everyone. It is my great pleasure to introduce Dr. Rajendra Pratap, who is currently working as Vice President and General Manager at Varbhi Semi Noida. Dr. Pratap earned his BTech from Indian Institute of Technology, Roorkee, his MTech in Vlsi design from the Indian Institute of Technology, Delhi, and his PhD from MNIT Allahabad. With over 3 decades of distinguished experience in the semiconductor industry, Dr. Pratap has held several senior leadership and technical positions across renowned organizations. Prior to joining Vlsi, he served as Associate Vice President at HCL Technologies, Noida, and as a head of the Noida Design Center at Infosys, where he lead advanced semiconductor design initiative and engineering teams. Dr. Pratap is widely recognized for his expertise in low power, mixed signal, and 3D IC design, with significant contribution to next generation semiconductor technology. Throughout his career, he has worked on several cutting edge innovation, including artificial intelligence and machine learning based hardware solutions, integration of silicon photonics with semiconductor chips, development of advanced 9-axis motion sensor system, etc. His technical leadership and vision has played a vital role in advancing innovation semiconductor solution for next generation computing and intelligent electronic systems. Today, we are honored to have Dr. Rajan Pratap with us to deliver an insightful talk on advanced Vlsi design and emerging architecture, AI chip, and neuromorphic computing. We look forward to an inspiring session as she shares his valuable industry experience, technological insights, and perspective on the future semiconductor design. Over to you, sir. Thank you for accepting the invitation. Over to you, sir. Thanks, sir.
Can you see my screen?
Yes, sir. Visuals.
Okay, so I have put this screen in full screen mode. So I will not be able to see anybody behind, but I would like to request that feel free to stop me. So you'll have to speak up and stop if you want me to answer any question while we are discussing about the topic. So is it better now? Is my screen clear?
Yes, sir. It is visible.
Hold on. Did something. Okay. Good afternoon, and thank you, Dr. Chandrasekhar, for giving me this opportunity to interact with the audience and who are working in the VLSI field. So my assumption is that the audience today knows about VLSI in general, what we do in VLSI industry. I am going to talk about a little bit kind of the advanced topic I am considering, because this is what is trending today in the market and in general in demand. Let me give a brief overview of my company. We are a small semiconductor startup, proud to say that we are the India-based only startup who is doing well in the industry. We very recently raised a Series A funding as well to grow further into our mission and vision. So we call ourselves as fabless semiconductor company, as same as any other, or in general, a lot of companies are there in the market which operate in the same manner. So fabless because we do not own our own fab. We go out and get the designs manufactured from industry leading fabs in the market. We specialize in the analog signal chain data converters. So our most of the products and IPs are around that domain. Our vision is to become the leading high performance mixed signal IP and IC supplier. So IP as well as IC suppliers from India. And the mission, we are continuously trying to foster it and achieve further, break further boundaries in this domain, is to build advanced analog devices for robust high-speed communication and sensor interface. So I'll show further the kind of products which we have, and we take pride in saying that these are one of the very much distinguished products in the market, because maybe very few people in the world you may find that very few people in the world will have similar or very close specs to what we have been able to achieve. For this kind of cutting edge design and technology, we hold multiple patents and trade secrets. And also we have very unique technology which is called as the machine learning technology within IC, which is around self healing and self correction. So very niche area to operate in. We are 60 plus employees spread worldwide, most of them 90% in India. And if you see within India also, we are like 80% in Noida, very few in Hyderabad and Bangalore, mostly in Bangalore, but very small in Hyderabad. So we have a lot of customer designs taped out, and that way hold a good proliferation in the customer base. We are privately held company. These are some of the products in which we are operating. We are operating in the weighing scale products, energy analytics related products. So metering, energy metering, and doing the analytics on the signals which we receive. We have very high precision, high gain, high dB ADCs and op-amps, which help us in doing the energy analytics, which are around, which are going to be coming in the market in next 2 to 3 years, where a lot of product companies are working, where they are trying to even detect which equipment in your home was switched off or on based on the analytics which our IC is helping them to do. So by sitting at the meter at the entry point of the energy which is coming inside the house, we will be able to predict which device was switched on, which device was switched off, and which one needs maintenance, and so on. So things like that are being done by multiple people in the market, whereby they are using our analog front end IPs and ICs for achieving those accuracies. Similar kind of usage is required in medical field. So we are having presence in the medical EEG and ECG acquisition systems as well, just because of the accuracy we are able to guarantee. Multi-channel data acquisition systems. So very recently we have done one chip for space. So this one is going to get used very soon in the next Moonyan or Chandrayaan being worked upon by our own space agency. Electric vehicles, battery management systems, and motor control products we have, where we have our own MCUs, which are being targeted for motor control. Even we got recognized by the government of India for doing the BLDC controller design. मैं आता हूँ 2 मिनट. अच्छा आप okay. So just give me one. Hey. Hello. I'll come back. Sorry, I just got this. Am I still there?
Yes, sir.
Okay. So we were recognized especially by the government of India for doing the motor control driver plus the complete MCU for the designs which are going to be used in the BLDC fan controller. We have, based on the accuracy which we guarantee, we have very, very high precision and sensor reference modules up to the level of 0.5 degree of sensing from within the IC. So those get recognized and used in multiple different products in the market. So we are recognized for such accurate analog front-end designs. Now, any questions? What is the format we are going to target? Can I take a pause and ask if there are any questions?
No, sir, you are going very right. Please be continue, sir. And yeah, I think your this PPD not visible.
What is not visible?
PPD.
Oh, okay. But earlier, was it visible till the time I was showing?
Earlier it was visible.
Though sir, it is a visible semiconductor revolution. It is visible, sir.
Okay, sir. Okay. I think I switch on another mode. Okay, sir. Thank you. Thank you. It is visible.
Okay. My pointer as well is visible?
Yes, sir. Pointer is also visible.
Thank you. Thank you. So let me now move to the topic of our interest, which we have chosen to talk about. Definitely the semiconductor is undergoing a lot of challenges, a lot of revolution, I would say, where things are changing at very fast pace. New architectures are evolving. AI is definitely disrupting the whole thought process. And in that disruption phase, where a lot of things are becoming obsolete, a lot of new things are taking shape. So definitely the chip design and the semiconductor domain is not. We cannot say that it is untouched. This is definitely undergoing a lot of different requirements and demands which are very rapidly rising, and AI compute demand is at the peak of it. What I mean by the first bullet is that so normal processors are kind of getting outdated. Well, they will stay in the market. It is not that they will vanish, but whatever new design is being asked by the customer, AI computation or the computation where the accelerators or inference or learning or something which is the artificial intelligence related requirement is very much in high demand. So we need those accelerators present in the CPUs, in the MCUs, whichever are being asked by the clients nowadays. In the past 2 years, I would say we have done multiple designs where this AI based compute resource was very much required and is gaining momentum. Now, having said that, that is also pushing the power limits because a lot of computations are happening in the background. Now, those days are like gone where you will have one peripheral, one MCU, and maybe a couple of other blocks in the chip. But there are multiple blocks which are running in the background, taking the data, doing some inferencing, doing some automatic learning, and that is basically pushing the power demand. So power is dominating, and this is becoming one of the biggest bottlenecks. So not only like you need to work upon reducing the power requirement, but also like, see, if you want these things to be present in the chip, there is always a limit to which you can reach. So then comes the second challenge, where you whatever is required, how you can provide it. So packaging your supply of the complete power delivery system, that becomes very, very important. So those things are dominating the whole analysis and whole design process. And now need domain specific silicons. So it is like what basically this bullet means is that we do not, or maybe there is very less demand or no demand is there, where there is a generic processor. uh, okay, give me a generic processor. So that generic thing is now kind of going away, and people are asking that, okay, why don't we dedicate this for a very, very specific particular application, whereby we are able to define what AI, what kind of learning, what kind of inferencing is needed in that module, what is the output expected from that chip, and how that chip is going to finally behave in the market. So custom design, custom in the sense not like the analogish design which I'm talking about, but the complete processor getting very much designed as per the specification or the domain specific need, to fulfill the domain specific need, that is taking a lot of like dominating the overall demand which is coming up. Moving further, so as I was explaining, microprocessors are now kind of getting obsolete. What is coming up is AI accelerators. So whatever you are trying to achieve, have dedicated hardware so that we can do them faster, so that you don't need like multiple cycles to do that kind of computation. Let's say if you are running multiplication multiple times, or maybe you are running 10,000 multiplication, so you need a dedicated hardware for that. You should not go through like multiple CPU cycles to achieve that. So that way AI accelerators are taking shape. Multi-core SoCs, now I'll show you some of the examples which I have. Multiple cores are there, huge number of cores are taking shape, including the AI accelerators. Now multi-cores with accelerators. So 2030 onwards, I would say that it will all be about how we do the intelligent silicons which are able to intelligently understand what is required to be done and do that is exact specific task. So there are two reasons for that. One, we are able to customize the AI for that particular requirement, as well as also reduce the cost. Because if you make general purpose CPUs, then your software development, your all that extra logic which is going to be sitting, which is not going to be used once that chip goes into the application. So because of all that, there is all going to be like cost associated with that. So that is why now the whole industry is moving towards intelligent and very, very specific requirements. Any questions up till now? Am I making sense?
Yes, sir. No questions, sir. Please continue, sir. After the session, we will ask questions, sir.
Sure. So you may see 3 nanometer, 2 nanometer, or maybe 1.8 or below 1. Also, people have started talking about, instead of FinFET, we have started getting GAFET, gate all around FET. And these are all not, like, I'm not talking about in research. These are all in production now. So people are able to get the chips which are going for the mass volume market. So process definitely is one of the factors which is helping in this way to achieve whatever the design is asking for. Design, as I explained earlier, it is going towards the AI or accelerator based designs. And since the designs are becoming complex, the verification is on top of it, most the complex thing, which we are not able to achieve that. Whatever technology exists today and the designs which are going out, getting printed on silicon, we are not able to verify completely, because of which we see a lot of bugs. And this is kind of killing us a big time. So verification is also like the challenge today. Manufacturing anyway is one of the biggest kind of challenge, where getting the yield, getting the whole thing packaged, managing the power is those are all those challenges which we are not able to scale up to as the designs are progressing further. So as I was explaining, AI is now there. We cannot ignore that. And to support all of it, see, you just cannot have the processor or the AI accelerator designed, and then once you connect, so you need to support the memory. So memories also need to be high speed. So high bandwidth memories, cores which are tensor or maybe the accelerator cores. And on top of it, NOC. NOC is like the network on chip, or basically the connectivity which all the modules have to be provided. So that is like becoming the bottleneck. So what I'm trying to say is that all these things put together, when they connect with each other, they should work seamlessly, and they should not waste the number of cycles, because at the end of the day, what we are trying to do is that we are trying to achieve faster computation and faster runtime. And if there is any bottleneck, anything which is stopping, which is taking more time, will kill the whole design. So all these things which are listed down here, they are kind of becoming are going through a lot of changes, and a lot of what do you call, new designs are being proposed. Even SRAMs. So now in-memory computes are becoming very, very common these days. A lot of experiments have happened around, and people are now ready to go into production with those new designs. So that way, even like the memories and the Macs, they are becoming completely analogish in nature. So that the bottom line, or the end of the day, what they are trying to achieve is that faster computation. And we should be able to do all that computation within that time, to guarantee and support all that requirement. All these things are undergoing these changes. Again, some of the considerations which or the targets or the specifications which come to us are like number of tops per watt, memory bandwidth, basically how much data it can take to and fro within what latency, and the int8 or FP16 trade-offs. So whether we should do an integer multiplication, integer calculations, or go to floating point calculations, and then also like the additional cost which it is incurring, or load which it is putting on the compute resources. So all these things are now becoming the architecture level requirements or challenges or demands which are getting kind of rethought upon, re-optimized, and redefined. With this, let me enter into a new domain which are kind of coming or taking shape. So CPUs, well, old thought. GPUs have become state of the art. NPUs have become state of the art, and not only NPUs. So even FPGAs are kind of undergoing a lot of architectural changes where instead of just having the traditional FPGAs, we should be able to do all these and experiment with our accelerators on the FPGAs itself. So the neuromorphic way of computation, the way we do the computation in our human brains. So people are trying to replicate that and trying to achieve those methods of computation. So I'll give you one or a couple of examples to show what people have tried to achieve. This is one product example, very complex. I am just trying to give you a glimpse of the complexity which this chip offers. This is available. This is TI's product. I have taken it from Google. So no trade secret or nothing proprietary item being shown here. The idea of showing this slide was to tell you that whatever I have been talking about earlier, all those generic things, now if you put this into a product form, see the kind of the product which is already there in the market. This is getting used. Now go through the block diagrams. You will see that this kind of complexity was put together and brought into shape and taken to the product market, which was targeted for high-end industrial process control. Now all these things are like you see there is a dual ARM core A72. That in itself is the A72 in itself is a high-end processor, but the dual core of it, 4x ARM Cortex R5F, just because it is an automotive chip. So you need that multi-core or fail-safe processing. So let's say if one processor fails, then there is another one which is working in the lockstep mechanism and can revive and help the vehicle reach to a stable and safe state of the complete process. Now imagine all these things, navigation subsystem, complete thing put into this. So this is one single chip. This is not a multi chip. This is one single chip which I am showing. Interconnect, which is providing the general connectivity with all the general automotive and in general board level connections which are given to the other peripherals. So you can see the simple connections, the SDIO, MMC, and UFS modules there. CANs are there, audio peripherals are there, and simple I2C and SPIs are there. ADC UART, I3Cs are there. Even like the Ethernet switches are there. So all of it was put together with a video acceleration. So taking the data from the camera modules and then processing. So this chip can even sit in the central processing zone or even the zonal processing unit, where so the way now the whole thing is getting designed, the vehicles are getting designed, is that they have a central zone or the controller, and then they have the zonal controllers. So whereby they basically the the front side will have, let's say, two processor, two zones, then the middle side will have multiple zones, and then the back side will have multiple zones, and then all of it, they coordinate together through the central zonal controller. So, and these kind of chips will go and sit in every micro or nano zone controllers, and will communicate and help in making sure that the processing is happening in real time, in sync with all the equipments or peripherals which are connected into the system. So gigabit time sensitive networking is very, very important in these kind of control processors. Security module definitely goes. So not only like the multiple security modules are present there, so that helps in achieving the best level of security for different communications which are happening in the system. So now think about it, why I wanted to show you that after talking about all the changes or maybe the challenges which are there in today's market. So imagine this kind of chip has already been productized, is already existing there in the market, and now people are working on the next level of integration. But even if you try and go and integrate this, so try and imagine the kind of challenges which this will pose, from design, from integration, from verification perspective, and then testing, board level testing. So even if you talk about like, even if you are able to design and get the silicon minted, how you will do the testing. So all of it requires huge amount of like effort, work, and next level of thinking. And I just would like to kind of trigger this thought process in people's mind that, see, this is what is required today, even to the next level. Not this is now the old design. Maybe the next level of thinking is required to achieve this kind of integration. Another very, very complex design, very complex design. This was for vision and sensor fusion chip. I'm not sure if you are able to read through the smaller blocks, but again, the previous one which I showed was definitely a big, huge chip, but this one is almost kind of integrating the double of what that one is doing. Multiple MCUs, multiple different processing units. There are multiple cores which are running, and then the caches, and then the interlocking. So they cannot run in isolation, they have to be interlocked. So all of it, and plus all this interface. So imagine what kind of, so this is more like a system, complete system on chip. And on top of it, this is SLD, automotive grade D level secure. Let me move to one of the next. This was recently announced, so I just thought maybe I'll introduce this processor to you, just to prove that where people are going. So these are going to sit in the laptops. So this was done specifically for the commercial compute market, where these are going to sit in the laptops and servers kind of compute requirements, where you see things like the CPUs, generic CPUs are there, but then on top of it you have GPUs, NPUs, accelerators, multiple accelerators, and then multiple IOs to accelerate or to support the data communication. So maybe let me kind of take a pause or try and reach to a point where we can take a pause and ask questions, and then I can move towards the closure of my talk. So this is like the maybe the second last slide which I have. So neuromorphic computing, which I was talking about, or in-memory compute, which people are now going towards. So these are basically driven by the way the human brains are working. People are able to achieve this complete thing. The way we have the designs, silicons available, taking going through the testing phase, and trying to see how we can, or where all we can improve the performance, so that we are able to productize it. This is the next level of integration, which I have done in multiple chips, and the the packaging is definitely becoming a bottleneck. So now imagine for these kind of chips, which are burning multiple amperes of current, how to even take that amount of power inside the chip, or maybe take the heat out. These are like becoming the biggest challenges today. The one which we did for a space application, there the currents are like reaching to almost like 10 ampere range, and how to even take that amount of current, and how to take the heat out, it's all uh, going through multiple experiments and iterations and evolutions to achieve finally what we want to achieve. So I'll take a pause here, and maybe would like to see if anybody has any questions, so that we can talk more about or understand the topics in better manner.
Yes, sir. My one question to you, sir, because you are talking about the neuromorphic computing, in just morning session, there even Professor Dr. Rajiv Ranjan sir from IIT Jindal. He was working in Memristar, and he have given a very good lecture. They have developed few IC, massive IC on the basis of Memristar, and they are working in the neuromorphic computing also. So they have given the lecture about the how Memristar will be useful for developing the neuromorphic chip and neuromorphic computing in the future. As per your lecture, some concept was there. You are using neuromorphic that is by using the recent industry trend. So in future, what Memristar can be helpful to replace this type of component to from this neuromorphic computing and other uh, recent or advanced IC.
Definitely. Let me touch upon some of the things which. I'm just going by my basic knowledge of Memristar. I do not have the details of what Dr. Ranjan would have spoken about, but neuromorphic computing, definitely what we are trying to do is that in within the let me give you the show, or maybe try to uh, explain you the challenge which people are facing. So you have the memory where you have the data stored. Now let's say if you have two arrays which you need to multiply. Now the two numbers are there which needs to be multiplied. You already have them stored. The next thing is you take it to the processor. Let's say if it is a multi-dimensional array, you take every unit to the processor, multiply it, and then bring it back and store it in the memory. So that is going to kind of take a lot of CPU cycles. Now, the other mechanism which people are trying to achieve is within the memory, you have the two arrays stored. So why not to run some kind of analog computation and then you have the sense amplifier, you have the bit cell, you have the bit cell. So let's say if you take a word together and do an analog digital to analog conversion, and then run through the analog multiplier, and then again do some kind of maybe a sense amplifier, so that quickly it goes and gets converted into the bit level and stores back at the same place. So this is more like I'm trying to explain how in-memory compute people are trying to achieve, and definitely memristor is playing an important role here. And with the help, if once it becomes like so, memristors become what do you call production friendly, yield friendly, these will definitely help in improving the overall efficiency. Because MRAMs and RRAMs, people have started kind of producing. There are yield issues, there are design challenges which people are facing. But if we are able to prove some of the things which are still in the theory stage, I would say that yes, definitely they are going to be very, very valuable and helpful.
Yes, sir, you are right, because this time, as per my knowledge, I asked this question to other professors also, because in this time, memristor is in the research phase, and many industry trying to develop the memristor the component level, but they are not going to be successful. So once I think definitely once this will come into the existence in the component form or in IC form, definitely this will be a great achievement for the semiconductor industry, and they will still replace the many of the components. Many high efficiency can be achieved by using the memristor also.
Very true.
And yes, sir. All right. Also, sir, I would like that yes, highlight few things about the chiplets and 3D integration. Few things about what this chiplets and 3D integration going to be. Recently, I've listened 2.5D also, and now I think this 3D is going on.
Yeah, see, there is a homogeneous integration and there is a heterogeneous integration. What now people are trying, and probably to some extent they have been able to achieve, is the heterogeneous integration. There are multiple reasons. See, the requirement is there. The justification or maybe the need is definitely there. So let's say for automotive kind of designs, you need a very high voltage, high power design where you are handling the high current part of it. Now, the computation part of it, you don't need that high voltage transistors and high power transistors. So that you will try to do or achieve on normal silicon based processes. So there are definitely the designs are going to exist on multiple dies. Even for those AI based designs or AI enabling accelerators, the kind of integration. So you cannot you cannot put everything on one single die. The die is going to grow like into a complete wafer itself, and then that like the power is going to be the biggest killer. So what people are trying to do, they are trying to divide those whole designs into smaller dies, because yield is going to be yield is one of the biggest challenges. Now, once you divide them, then how you basically integrate them together, so stack them together and then achieve that stacking. So there, if you see the FPGA stacking, which maybe fortunately I worked upon this product from Xilinx when I was at Xilinx. So there they have done very good work where they have been able to put multiple individual FPGA fabric chips as individual dies, and then put them together using a interposer, and on top of it put multiple gigabit transceiver, so communication, and then the analog portion of it. So see, the different kind of designs are going to exist where integration of them together will be required, and one of the probably feasible ways which is getting proven successfully by different people is this 3D integration. So 2.5D is like where you make use of the interposer and put together the design and stack them on top of each other, so maybe 2 or 3 layers. And then there are those heterogeneous design integrations where you stack dies on top of each other and then try and get the whole thing packaged into a single package. So these concepts have existed earlier also. Multi-chip modules were already there, but yes, now the integration level has increased, whereby chip scale packaging is now possible, which has really enabled or helped in larger integration through packaging evolution.
Right, sir. So definitely, I think now industry is working in 3D integration this
Yes.
time. Nice.
Lot of products are already there. We already have production proven designs and packaging towards 3D.
And we see that in year 2030 government mission, we will be able to get completely on the 3D integration, and will be move for another level of integration. Any question from other side? Yes, sir. Please.
Yeah, please.
Any question from the other side, audience? You are very.
I'm Yatish here. Good afternoon, sir.
Very good afternoon.
Sir, initially in the presentation you told about fabrication. Is there any company or person we students can approach, give their GDS2 file and get the IC chip fabricated in India?
Yes, sir. Now, definitely this is possible, and let us work together. I would like to maybe I will be more than happy to help you and get this whole thing done. A lot of people are now getting this done, and this is, yes, maybe 2-3 years back, this was not easy, and people were not able to, or especially the students were not able to get their designs printed. But yes, definitely. So let us connect back. There are multiple different ways to get that done. We can work together. So there are actually there are multiple levels of challenges which needs to be understood, and probably that is the that is part of that whole process which students need to learn, so that they understand and get the design fabricated, packaged, and then bring their designs and test them. So yes, sir, now it is possible, I would say.
Thank you. Thank you.
So my email ID is there with Chandra sir, and we can connect back. Yes.
Right. Sure, sir.
Sir, I would also request you, sir, in future, if our students approach to you, or some internship type of process held in your company, so we can request you that our students want to do some industrial training in your company, if you are permit this. And also we request you to visit our campus sometime. So this type of facility, this type of knowledge that can be verbally in the front of students, we can share with you, because in this online session, there is a limitation, because students do not think that how much these things are very much important. So in front of students must be present. Definitely they will come to learn, and many things they understand that what industry trends are going on. I will request you in future that you should visit to our campus. We also request to our management that create the facility that such experienced industry people should come in our can come in our campus.
Sir, this is my last slide. I would like to give my email ID also, so that it goes to all the audience. Can you see my screen?
Yes, sir.
So, sir, more than you, I think now as an entrepreneur, as a startup owner, I would say that there are a lot of things which requires academic support. Without working with the academia, there are a lot of experiments, there are a lot of what you call innovations cannot be achieved. So there are fund limitations, there are monetary limitations, because of which we need academic support, and joint R&D between industry and academia is unavoidable, I would say.
Definitely, sir. We will look forward to make a bridge between the our campus and your industry and semiconductor industry, so that our student and our faculty can get benefit from you.
Very, very much, sir. Very much, very much.
Any message from you to our students? What should they learn? What should they do? What they should achieve in the camp from the engineering level, so that they can get the approach for the industry level of recruitment?
I would say that, see, the reason for showing all these slides today was exactly that same thing. Try and go through the new products which are getting announced and designed by different companies. So that way you will get an exposure of what is happening in the industry today. So going through the latest, if you are in the chip and design, VLSI or semiconductor industry, whichever area you are focusing, even on the design or packaging or verification or analog or digital, whichever area. So try and go through some of the latest recent publications or the work being done by the industry. That way, if you are up to date with that knowledge, so absorbing you, or maybe getting introducing some problem to you, will become much easier. So that way it will be very easy to kind of initiate some work and experiment on some of the problems.
Thank you, sir. Any question from audience side? Now I'm going to finish this. Any question? So now we are at the end of the lecture. I extend my heartfelt gratitude to you for delivering such an insightful and engaging session on advanced VLSI design in emerging technologies, architecture, AI chip, and neuromorphic computing. Your expert presentation provided participants with a comprehensive understanding of the latest advancement in VLSI design, growing importance of AI accelerator, and the transformative potential of neuromorphic computing. The way you connected fundamental concept with current industry trend and future research direction made the session highly informative and inspiring for our faculty member, researcher, and student. Thank you very much, sir, for accepting our invitation and delivering such a wonderful lecture. Thank you, sir.
Thank you very much. Thanks to you and to the audience and the organization. I really appreciate such initiatives, because they provide a platform to come up and hear some of the thoughts of industry leaders, as well as this may trigger some idea. So that will be the achievement of this overall effort.
Sir, we from Department of Electronics and DSS University, we also request you please visit our campus one time.
Definitely.
We will send you invitation very soon. Thank you, sir.
Sure, pleasure. Thank you. Thank you, Dr. Chandrasekhar.
Thank you.
Thank you. Thank you. Can I disconnect?
Yes, sir.
Thank you.
Please.
Thank you, sir. We now move on to one of the most anticipated sessions of today's summit, the panel discussion on the theme, Can India Become a Global Semiconductor Hub? For this session, let me invite Dr. Chandshankar and Dr. Amit Kumar Ahuja to introduce our distinguished panelists and initiate the discussion. Over to you, sir.
And looking at our panelist, Vijaya sir and Ravindra Jha sir, are you there, sir?
Yeah, so I am there. Vijay is there.
Good afternoon, sir.
Good afternoon.
Thank you for joining, sir.
Thank you very much for giving me opportunity to speak to all of you. Okay, industry academician and all the best professors. Okay. Yes, Chandrasekhar, it's glad.
Ravindra sir, I think he said that it's usually the planning, instead of planning. Just a second, sir. I just confirm from Ravindra sir. Very soon we are going to start our session, panel discussion. Good afternoon, Ravindra sir. Good afternoon, Vijay sir. Am I audible to all of you?
Yes, yes.
So today we are
Good
going to start
afternoon.
sir. Good afternoon, sir. So good afternoon, everyone. So now we are going to start a panel discussion here today with us, Dr. Ravindra sir. He is assistant professor in Department of Electronics and Electrical Engineering at IIT Guwahati and is associated with the interdisciplinary program in health, science, sustainability, and design. His research focus on semiconductor device beyond silicon electronics. Prior to joining IIT, he served as scientist at CSIR, Central Electronics Engineering Research Institute, Pilani, where he worked as a nanobiosensor and microsystem technology. He obtained his PhD from IIT Kharagpur and subsequently carried out research at the Indian Institute of Science, Bengaluru. He is a recipient of prestigious fellowship, including D.S. Kothari and SERB National Postdoctoral Fellowship. Dr. Jha has authored over 100 peer-reviewed publications and delivered more than 100 invited talks at national and international forums. including leading IEEE Sensor Conference. He is a senior member of IEEE, a governing council member of ISSS, and founding chair of IEEE Sensor Council, Kolkata section and Guwahati subsection chapter. Welcome you, sir. My another panelist is Dr. Mr. Vijaya Kumar ND, sir. He is a director in Proxilera India PVT Limited, Bangalore. He is a senior professional in physical design with over 24 plus years of experience in leading MNC and significant practical experience in designing various unique device design flow, establishing ODCs, design center, compliance and setup and auditing. He has a vast experience of many semiconductor industry throughout the career from 1991 to 2023. Welcome you, sir. So, as a moderator, I am Dr. Chandrasekhar, Associate Professor in Department of Electronics, GSS Academy of Technical Education, Noida, now becoming GSS University. I'm going to start this panel discussion. Before going to start, now I would like to introduce few things about this panel discussion. As India has emerged as one of the world's largest semiconductor design destination and is making significant investment through the India Semiconductor Mission. However, becoming a global semiconductor hub requires much more than chip design. It demands world-class manufacturing, advanced packaging, research excellence, skilled manpower, and strong collaboration between the academia, industry, and government. To discuss these opportunities and challenges, we are privileged to have with us two distinguished experts representing both academia and industry. I warmly welcome Dr. Ravindra Jha sir from IIT Guwahati and Mr. Vijay ND Director Proxilera, Bangalore. So my first question to you, to both of the panelists, what milestone should India aim to achieve by 2030 to establish itself as a leading semiconductor nation? Over to you, sir. Dr. Ravindra, sir. Can you please give some brief or about this mission?
So, yeah, good afternoon, Chandrasekhar ji. I mean, this is very important question for everyone, including, I would say, academia, then industry, as well as, of course, the people of our country. Okay. So, I mean, of course, I have the liberty to talk only from the academic point of view. Okay. But as far as my understanding is concerned, I mean, when you say a milestone for semiconductor, I mean, leading something in semiconductor, okay, maybe by 2030, or since your topic is 2030, maybe beyond 2030 also, okay. First of all, the intention should be to be part of this, value chain, okay. So I mean, it's a complete ecosystem covering from say chip design to say ATMP, wafer fabrication, testing, reliability, supply. Many things are there. Okay. So first of all, in my opinion, we should enter this. We are going from say we are taking kind of top-down approach. We are first entering into ATMP, which is a very nice step. You might have seen that India Semiconductor Mission is also launched. 2.0 is recently launched. Okay, so these things will definitely place us in the semiconductor value chain. Okay, when you say leadership, I still believe that in the chip design, we can definitely lead, because if you talk about fabrication and all, I mean, everyone understand that it take time. Second thing is the research and innovation that we are doing, particularly if you see, if you remember what I was talking in the first half of this summit, I was talking about 2D material based devices. which is of course a kind of research everywhere. Maybe you talk about Europe or you talk about US or any other country where everyone is trying to uh, compete and race for this particular technology. So this is the bus, if you see, we can take. Of course, if you see Europe's graphene flagship or UK's flagships, which was hosted at Manchester and Cambridge, or you see US where there are different consortium of 2D material formed with Penn State and other universities. Okay. I mean, Government of India has also launched very recently a 2D innovation hub in India. I think this is the right bus. So, along with chip design, research and innovation is another aspect in the you say semiconductor line where we can get into. Okay, we are already, I mean, several our country has been able to attract several talents from those places that I have mentioned to our country. So means that they are able to provide that kind of facilities, to them to take the R&D forward. Then another thing, I will not take much time. I don't know how much time you are giving to each panelist, but I will just take a minute and then I will stop. Okay, because you might have more questions lined in. So, second, the last point that I just wanted to mention is about the our engineers. We have very good universities and institutions which are producing good engineers over the time. I would not comment from the quality and quantity perspective that I am sure that every universities, including ours, are looking into every day who want to graduate bad engineers. Everyone is pushing to produce good engineers. Okay, of course, we all can come together and maybe uh, 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 seeing the curriculum of foreign universities or some industries where this kind of industry academia collaborations are there. Like I have one example in the form of NTU Singapore, okay, where you have a very nice you say efforts being made to have everyone on board and then develop your talent accordingly. Okay, but of course talent shortage is there and always be there, but in Indian engineers are someone where where we are able to produce several world class talents. So this is another front where I can say that we will be able to lead by 2030 in terms of manpower. Okay, yeah, so that's all from my side. Yeah.
Sir, and I would like to listen from Vijaya sir. In the
Yeah.
terms of industry perspective, what should be the mission milestones should India need to achieve up to by 2030?
Okay, thank you. Thank you, Chandrasekhar, for giving me opportunity to speak to the world-class professors. And as Ravi sir mentioned, Professor Ravi and mentioned, so there he has covered most of the things with reference to academia and industry, and also the some of the very important policies which the current government, okay, have been putting more emphasis on the semiconductor mission and the semiconductor possibilities. How can India become a global hub? Okay, like software, right? So the same thing we are also the government as a part of their panelists and all they are discussing with various industry counterparts. They have set up with ISM 2.0. They have come up with a lot of good strategies. So those good strategies are very much, yeah, at par, and they are focused on the requirement which India needs to go into the 2030 milestones. But that is not itself is sufficient to get into the we are the global players in the semiconductor industry. So there we can see that. So we are starting Tolera. Okay, that means the Tata is coming up with a huge plant which can focus on 28 nanometer production, chip fabrication, and we are also starting the OSAT. Okay, and the ATMP. The facilities got established. It will be established in Assam and all. So they are good. They are good starting point to add to, but it is not very sufficient fueling. Okay, it is not sufficient points which needs to be covered. So there are a lot of things, as Dr. Ravi pointed out, the talent pool, the innovation, okay, and all the facilities. That means the entire ecosystem needs to be built. So the entire ecosystem in the semiconductor mission means what I am thinking or what I am telling you front as a industry person is that we need to not only the fabrication unit, but we are talking about if you see any newspapers or any journals, we are talking about 2 nanometer, we are going to angstroms. Okay, we are working on 12 angstroms, right? So and whatever we are doing in India, okay, it is to the starting point. We are having 28 nanometer fabrication foundry unit we are coming up with, and there are a lot of incentives which the government is giving it. And so what I meant by ecosystem is that we need to have a one shop or one solution for entire fabrication. Okay, that is the foundry plus ATMP and OSAT. Okay, and also the fabrication, the ecosystem needs to be built in such a way that we need to have a foolproof talent. Okay, innovative ideas, very good companies. Okay, and also the materials which are coming up for the foundries. It's because if you see the chip fabrication or the foundry, which we need very good ultra pure, okay, ultra pure AC air, and also the ultra pure water. Okay, and also the fabrication unit which needs to be coming up with the extreme ultraviolet lithography process, right? It works on the photolithography process. All those things. That means starting from the fabrication and what all the equipments which are coming in the fabrication or in the foundry, that needs to be provided, that needs to be imported. And those things, if we build it by ourselves only with the Atmanirbharata, okay, so those kind of things, so then we can become a very good pioneers, okay, very good master in the current scenarios. That's what Dr. Chandrasekhar.
Sir, what skill set or skilled workforce are required for achieving this mission in terms of engineering graduate or experienced people, those who are working in the industry? What skill set they will require to achieve this mission?
So you are asking me, Doctor?
Yes, sir. Yes, sir.
Yeah, okay. So yeah, that is a good question which bridges the gap between the academia and this one. So because there is no dearth of engineers as far as the designing is concerned, okay, chip designing, we have been pioneers, and most of the chip design activities are about 30 to 40% of the entire global, the chip industry. We are working through our Indian folks only. So, but the main problem is the for entire ecosystem, as I mentioned, right? So we may need very good engineers, okay, who can understand the process, who can understand the techniques, who can understand the material science, who can understand, okay, who can understand the activity of using the very expensive, okay, and very advanced tool sets or the advanced foundry equipments. So in doing those things, we have been we are lagging in that one. So if we have collaboration with some of the good companies, okay, TSMC. Now, I have heard that there are a lot of collaborative work which is going on between us, our country, and TSMC. They are also extending the training programs and all. If that is coming and if it is introduced as a one subject or somewhere, it gives the young engineers, okay, young engineers with that kind of talent, then it will really help. So I hope I answered your question.
Yes, sir. Yes, sir. My another question, sir. What key factor that will determine India's success in building a globally competitive semiconductor ecosystem? Means a lot of countries that already existing their ecosystem, their industry environment, but India is just putting the steps towards this market. So what India should do that they can do a globally competition in the semiconductor ecosystem.
Okay. Yeah.
Vijay sir.
Yeah. So what are the key factors? So as we have entered into, there is a very good starting point. We have started with the Dholera plant, where we will be starting with Dholera, and and also some plant will be coming with OSAT and ATMP and all those things. And we have also have the very good collaborative work, and they are also coming with the fab with Micron Technology company also. So as I mentioned, as a leadership is concerned, from the Indian perspective, these things are going on with the phase, whatever is requested by our youngsters. But that is not sufficient, as I mentioned. The key factors which determine India's success in building the competitive semiconductor ecosystem is we are there in manufacturable capability. We have started now, and to fuel the manufacturability or the manufacturing capability is one of the important thing in which the Indian government has entered into the what are the things which are going on in a good phase. But that is not sufficient. We need to have a complete ecosystem for the establishing the advanced package facilities. Multiple PAPs needs to be. Now we will be depending on only the few PAPs, but we need to come up with a different collaborative work with the private PPA model kind of thing. And a lot of private entrepreneurs should come forward and start, because the government is giving a lot of incentive, a lot of promotional activities are they are giving. And also some of the things which are required for the manufacturing capabilities, that we need to have a uninterruptible, disrupting 24/7 reliable power. Reliable power. We need high quality water supply. High quality means very purified quality water supply, and world class industrial infrastructure. So that's what I meant. So world class infrastructure, industrial infrastructure which supports the semiconductor manufacturing is very, very much needed. And so, because why I am talking about this is because we are in 28 nanometer. When you come to the advanced nodes like 7 nanometer or 5 nanometer fabs, all these things, what all the infrastructure I mentioned, right? That plays a very key important role in these kind of thing. Okay. And also, as the professor mentioned, the talent development will be a critical differentiator now. So India already has a strong semiconductor design workforce. As I mentioned we have a very strong standard and very proven semiconductor design workforce. The entire world has appreciated these things. We are there. We need large number of process engineers. That's what I want to say. Process engineers, equipment specialists. Okay, as we are talking about very lower nodes, means we have extreme ultraviolet photolithography process, and analyzing those things, etching process, photolithography operations, everything will take place. And also packaging engineers, technicians, and researchers. So most researchers who are working in the advanced nodes, who are working in these things, are very much required. So that's why. So my emphasis is that. So it is not possible with industry alone. It is not possible with academia and persons only. It is not possible. We need to have a strong collaborative model, or wherever the gaps are there between our young bloods and young talents. Okay, we have tremendous things will be there, tremendous aspiration will be there in the young engineers, but they are lacking with the practical exposure. So those practical exposure we need to build in, we need to fuel in. Okay, by having a collaborative work between the industry and the academic. Okay, so then all those gaps will be filled, and who are coming out from the college, so they will be industry ready means, so if they have some good internship programs, and with 1 month or 6 months training if we give it, so then they will become the seasoned engineer, so that we can take it into the actual project and the fabrication work kind of thing. Okay.
Yes.
So those are the things, Professor.
Yes. So I think you have answered my next question that I want to ask is how can academia, industry and government collaborate with more effectively to bridge the semiconductor talent gap in India? The same question is this question from Dr. Ravindra Jha sir. So how can academia, industry and government collaborate more effectively to bridge the semiconductor talent gap in India?
Okay. For that, I would say ki, like we get different projects from government. Okay. From the inception of the project, maybe what should be the idea that project should come from industry. They should come up with the problem that okay, the thing is that rather looking for the problem statement, or say rather looking for solutions from outside the country where things might be available, we might not be that ready. uh, Industry also should take some pain, and of course, if they are not taking, government can help, and then they can sit together with the like what I mean to say ki all the three parties should sit. Industries should define the problem that okay, this is my problem. If you solve this, I can save this many bucks which I am investing on importing something. And anyway, government is putting a lot of efforts in giving money for R&D projects. That money can be given. Maybe see, industry may not be, because it runs on profit. It's not key. They will keep on giving R&D projects. So government is giving the money to the academicians, and maybe I'm talking right now only about academicians, but then I have also worked with CSIR kind of lab where the focus is on solving industrial problem. Okay, so so these people should sit together. They should make team, and the party. The R&D team should be able to say, ki, okay, they are able to take up the project or not right away, or maybe they can take a month of time or 2 months of time. So industry should not be asked to put any money unless and otherwise they are willing to. Of course, once the solution is ready, industry should see if that problem, that solution is viable for them or not. If it is not, again some iteration should be there, and accountability maybe during the project progress and other places, accountability should be fixed. And I know several of my colleagues who have a lot of experience, and they are ready to take up any kind of industrial project. But industry is also not that ready. But what I would say ki it's not their fault. It's ki we might have not, academician might have not solved their problem in past, so they might not be interested. But the government's focus is like is on startup, make in India, digital India, self-reliant India. All these things actually require the root is made in India, right? So if you go in that sense, we have of course done very good in all the R&D. If you see, there are just you sit in your office and you see around, you will find n number of things which our country has taken, a lead with world leaders also. Maybe except this electronic thing, if you see some metallic thing or metal processing or many places, we are far ahead of many countries. Food processing, many places. Okay, but in this, why we are lacking? Because we have not come together. Because see, initial cost in putting up this R&D facilities are also very high, right? That's why you know that we are not able to even have visit to clean rooms, or even a small clean room visit is like a win-win situation for several universities. There is a visit of our student to this clean room or that clean room, because initial investment is large. Okay. Since R&D Institute has already housed this kind of setups, I think maybe some of the solutions can be provided in house, and along with this, second important thing I would say that we should not only look for big players. Our MSME should also get involved, heavily, because MSME has semiconductor, as I have mentioned in the morning session also, require a lot of material. Last semicon, maybe it was in Noida only, if I remember. I visited the Tata packaging counter and then other, kiosk, and I found that around 50 to 70 companies, mostly dominated by Japanese companies, were visiting just to be part of the supply chain of the packaging plant that is coming to in Jagi Road. Okay. Our institute is also getting ready in that way, that along with the packaging, there are 70 different companies which required to be part of the supply chain. Okay. To come up with a good academy, industry, and government partnership, I think policies will also make very important role. Like Vijayji was mentioning that industry require, particularly this kind of industry require clean water, it require good power supply and all. Okay. These can be, I think, one point solution for all these things are government policies. Okay, many government, including our central government, have that kind of policy, and they are providing a lot of support to all these business people. But I hope that the deadlines that you have given, I think by that many things will be ready, and of course, you will see many industry. I have met people. I mean, I can't name those companies, but the process engineers, they are looking for process engineers in our country. And this is the first time I have seen that big companies looking for process. They visited us also. Okay, they are, looking for process engineers. So yeah, talent and other things is something which we have to develop together with industry and government. Yeah, that is all I want to say.
Thank you, sir. Give you a very brilliant answer. And as per my understanding and discussion with you and Vijay sir, means there are three stacks. Means one is the university where student and professors are there. Another thing is the industry where the industry leaders are there and their employees there. And third thing is the government where many sectors, MSME like MSME and this millet and many organization that they are working in the semiconductor systems. So definitely there is a gap in industry and the academia. Means just a few days back, I attended a semiconductor conference in PhD House, New Delhi. They were focusing, the conference was on the same semiconductor ecosystem, government policy, and all the things. And definitely this government have launched ICM 2.0. So one speaker from industry, and he said that because at university level, professors are doing a lot of work in the terms of research, but in the terms of industry, they are not able to solve the problem what the industry is going on. They are doing the advanced research, and students, as per the syllabus point of view, their topic to teach the student, they are 20 years back. Now, in this gap, what we can do, I think, as per your this explanation, that if government play a role between to bridge the gap between these two, means industry and academia, if they facilitate the the need, as per the need of the industry, if they facilitate this thing to the university level, they create the lab like foundry lab or advanced equipments required for the semiconductor for assembling or OSAT. If this facility, as per the industry need, to be created at the university level, this way, I think they can bridge a gap. But definitely, the trend people from the industry, they will come to the university level, good university level, and so that they can create fulfill the gap between of these two. Maybe this may be helpful because this question is always arise.
Yes.
I agree with this.
Yeah, I do agree.
Thanks, sir. So my next question. Now, sir, how will emerging technologies such as AI, automotive electronics, IoT, 6G influence India semiconductor ambitions? So, how these technology play a role in the India semiconductor ambition, like AI, automatic electronics, IoT, 6G, all the things? My question to Vijaya, sir.
Okay, yeah. So it is a very great question now. So because we are talking about in all part and parcel of life, we have become AI. AI is killing our jobs. So where are we standing? Where we will be there after 5 years or next year? So a lot of confusion among youngsters and AI and machine learning. Okay, so ML and all those things are very very hot topics. Okay, which are heard from everywhere. And so now, as we are already mentioned by Dr. also, so the artificial intelligence, which plays very critical role, and everywhere we go, so this AI is emerging. Okay, and in the AI in the semiconductor industry is also a very very important need. Okay, important need for the building the advanced chips at the very lowest time period. That means the turnaround time should be very less, and that is possible with AI, very powerful AI machines. Okay, wherever the reusability, wherever the redoable things are there, which we can set automation through AI, and we can plan, we can train those things, whatever the repetitive task to the system or a powerful data center, and that will take care of all those things, the repetitive task and some of the manual portions which can be taken part by the machines are the very powerful servers. So to answer your question on the these different domains you have mentioned, they're all, we can call it as a different semiconductor domains are they, as far as the their application is concerned. So AI, for developing any AI, okay, we need very powerful chips. Okay, so that means, so there is a word in the semiconductor industry that AI for chip designing and chips for AI. Okay, so these, it goes complementary. That means to generate very AI powerful machines, we need very advanced chipsets. So we are talking about NVIDIA chips. We are talking about very influential GPUs, very influential NPUs. Okay, with Google, AMD, and Intel, they're all Qualcomm, they're all coming with very advanced chipsets for supporting the AI and the different models, which there's a lot of terabyte operations should be completed per second. So these are the requirements, the current industry requirement is there. So that's why the semiconductor domain, so these AI operations are working in a 2 nanometer and in angstrom technology nodes, because they need they should operate at say 50 gigahertz frequency. Okay, we are talking about 10 gigahertz frequency. So those things are possible with the advanced nodes. And coming to the second one is automotive electronics. So in the automotive electronics and electric vehicles, it falls a very key domain in the current semiconductor industry is concerned. So a lot of companies like NXP, okay, Microchip and all, they're working on those Infineon, for that sake, they're coming with MCUs and very good controlling units. So there, where the requirement is that we are building the ADAS, okay, autonomous driving assistance system. So that means we need to have a coordination. All those things will come into picture. So in that autonomous vehicles also, we need these kind of chips, wherein which can operate at higher nodes like 28 nanometer, as we mentioned, right? All those That's why our Indian semiconductor companies, okay, Indian semiconductor hub, whatever we are building now for 28 nanometer, so that can be taken care of all these chip producing applications for the autonomous and the automotive industries. And the third one you mentioned is the growth of Internet of Things. Now we are from the office only. We can connect everywhere. Okay, we have talked about CCTVs and CC cameras. We are talking about the smart cities. Okay, smart technologies, smart devices, smart connected devices, all those things. So that also a lot of scope. So is there. So in this IoT means we need to have powerful sensors. Okay, powerful transducers when the sensor, and a lot of IPs needs to be used in the semiconductor domain for catering to IoTs. And lastly, we are coming to 6G communications. So this also plays very important role when you are talking about 6G, where when we are there in 5G, a lot of activities are there, and we are having the very high speed network internet is connected. Okay, and in that we'll have the very high bandwidth, the mobile network, high bandwidth, what do we call the set-top box, okay, high bandwidth, the routers, everything is possible. So in this, lot of networking chips, high speed processors, and specialized communication semiconductors are coming up this one. To answer to your question, the Broadcom, okay, Cisco and Qualcomm, they are playing a very dominant role in coming up with these specialized chips for supporting these 5 6G, and also Nokia, okay, they are coming with for supporting this 6G communications.
Sir, thank you for the brilliant answer. Ravindra sir, any discussion about this AI automatic electronics as per the academic point of view?
So, Chandrasekhar ji, are you asking me?
Yes, sir. Yes, sir. This is our last
Okay.
question.
Yeah,
We are running a sort of time.
missed it.
Yes,
I'm
sir.
sorry. Yeah, quickly, can
Yes,
you
sir.
repeat it?
So the question is
yeah.
just now Vijay sir explained about how will emerging technologies such as
Yes,
AI
yes.
or automatic technology,
I was there.
IoT.
Yeah, yeah,
So,
yeah, yeah.
so these
So,
technology play a influence India semiconductor mission. How these technology influence the India semiconductor emissions?
okay. So you want my opinion on this?
Yes, sir.
Okay, yeah. So, I will not, sir has already mentioned all the important things. I would take it in other way, like advanced technology. I would also include one AR VR thing here, because that is very crucial for giving you a feel of working in fab by sitting in your room. Okay, so I know one company which is working on advanced AR VR tool to train manpower to work inside a clean room. Okay, so if you go inside a clean room, and if you are not trained enough, you may end up making some mistake and end up destroying some a few $100s. Okay, however, this AR VR tool, which I'm sure these companies are going to use, or some of them might be using also, okay, are very, very effective. Okay, you can wear that and you can fix, like for example, say if you are using say advanced sputtering system, for example. Okay, by using that AR VR tool, you can exactly virtually change the say sputtered target. Okay, that you might have done actually in the lab, in the fab lab. Okay, similarly, you can do all the photolithography or say e-beam lithography steps virtually with advanced simulation tools available. Those things are quite possible in virtual mode. So if you have that kind of advanced technologies, of course, all this AI and machine learning can be used there. For example, say if I am training a person A and person B together on that virtual machine, okay, by machine learning, I can train my model, to understand that what mistake that person is doing. Okay, and by finding out their mistake and training over the time, he can be, trained to rectify those mistakes, making you foolproof before he actually enters the clean room. All right. Like we know that although in wet base, but we require, as a process engineer, we require, to deal with several acids. So first step we have to do is we have to write an exam to enter in a clean room. Okay, a safety protocol exam. So you have to deal with hydrofluoric acid, which is very dangerous. Okay, although sometimes you deal with buffered, but then sometimes it is not buffered also. Okay, so in that scenarios, if you have virtually identified that this particular acid that is lying just besides you can be that dangerous, you can see its after effect virtually, you may have made mistake. You will have that particular kind of knowledge that okay, how you should behave inside a clean room. This is just one aspect that I'm touching up because of the time constant. But yeah, there are other places also where this modern technologies, including AI and machine learning, will be helpful. As a hardware engineer, I believe that sir has also mentioned that these technologies are not going to make me irrelevant. They are going to just assist me in executing my job. So I am considering this all technologies as my another tool. I am not considering it as a threat to my say job or something. They are just to assist me. Yeah, that's my opinion.
Thank you very much, sir. So now we are running the sort of time. So now my concluding remark for this wonderful panel session. Thank you to both panelists. So the today's session has clearly demonstrated that India possesses many of the essential strengths required to become global semiconductor hub, a strong talent base, a thriving chip design ecosystem supporting government initiative and increasing international partnership. At the same time, achieving this vision, we require sustainable investment in the fabrication facility, advanced packaging and testing infrastructure, research and innovation, and close collaboration among academia, industry, and government. The insights shared by Dr. Ravindra Jha sir and Mr. Vijaya Andy sir have highlighted both the opportunity and roadmap for realizing the vision of Silicon India 2030. On behalf of GSS University Noida, I extend my sincere gratitude to our distinguished panelists for sharing their expertise and valuable perspectives. I also thank the audience for their active participation. Let us continue working together to build a resilient, innovative, and globally competitive semiconductor ecosystem for India. Thank you very much, sir. Now, our next session is going to start. Our speaker already joined. And now I request to uh, Madam, please introduce our next speaker.
Okay, thank you very much.
As we approach the final technical session of today's summit, we are delighted to conclude our series of expert talks with another inspiring session on advanced chip design technologies. It is my pleasure to invite Dr. Sadhana Kumari, Assistant Professor, JSS University, to kindly introduce our distinguished speaker for this session. Over to you, ma'am.
It is my great pleasure to introduce our distinguished resource person, Mr. Chandan Jha, Chief Technology Officer of OG Silicon. Mr. Jha has over 15 years of rich experience in the semiconductor industry and is currently leading the development of mixed signal, physical and DSP technology for next generation connectivity solutions. Throughout his career, he has made significant contributions to the design of physical layer silicon for Ethernet physical layer, high-speed ACRDES, wireless communication system, and coherent optical DSP for terabit class communication links. His area of expertise include data converters, equalization techniques, and analog mixed signal behavioral modeling, making him a highly respected professional in advanced semiconductor and communication system design. Before joining OG Silicon, Mr. Jha held key engineering position at MediaTek, Global Unichip, and Infineon, where he contributed to cutting-edge semiconductor technologies. He earned his master from science in electronics engineering from the National Chiao Tung University, Taiwan. So this is session introduction. Today's session explore the exciting world of semiconductors, the invisible technology that powers our modern lives. Every message we send, every vehicle equipped with advanced safety machines, and every AI-powered application we use depends on tiny silicon chips working behind the scenes. In this talk, Mr. Jha will take us through three major technology frontier that are transforming the semiconductor industry: 5G, 6G communications, the Internet of Things, and automotive electronics. While these fields serve different applications, they all share a common challenge, that is moving data reliably, efficiently, and at high speed. The session will also examine how the rapid growth of artificial intelligence is reshaping the semiconductor landscape, dividing innovations in advanced transistor technologies, chiplet architectures, and custom silicon design developed by foundries and fabless semiconductor companies. Finally, Mr. Jha, this much is me. So, without further delay, let us welcome Mr. Chandan Jha for his insightful talk. Please join me in extending a warm welcome to Mr. Chandan Jha. Over to you, sir.
Can you hear me?
Yes, sir.
Okay, I'll just share the screen. Is my screen visible? Okay. Okay, thank you so much for inviting me on this summit, and thanks Professor Chandrashankar also for inviting me. Uh, uh, My session, you will find that is very much in continuity with the panel discussions that I fortunately got to listen, and there were very nice, insightful discussions and viewpoint. And my session is also kind of continuous to that, where I will be trying to briefly touch upon 5G, 6G, IoT, automotive systems, and maybe data center chip design aspects. And my focus will be on what are the process that a chip design from spec to tape out goes through. Briefly, I'll touch upon that, and how we can work together with the academics or the universities, and how we can build employable talent. So the thing is, why I started OG Silicon is because I have believed in Taiwan for like almost 16 years. I have seen how university graduates, as a university graduates, we move to industry. But then the things 16 years back, I found that what we learned there are some missing dots between what we learn at the university, and then when we do it in the industry, it's little bit different sometimes. But what we carry from the university is a strong foundation on the fundamental courses, whether it is in analog design or whether it is in DSP design or it is in software. So carrying on that, so for example, for as of now in the current generation of technologies that are coming up and that are being developed by the industries are in 6G, 5G has already been deployed. And for the IoT, if you consider Wi-Fi, Bluetooth, or maybe low speed Ethernet, like 10 mega, 100, 10 mega, 100 mega. Now, the Ethernet has also moved from 4-pair to single pair, and many companies such as like NXP, Microchip, and Broadcom, they're already working and producing millions of chips every year on the single pair Ethernet. And then this single pair Ethernet for the high speed like 1G, and also like companies are developing 2.5G, 5G standards on single pair Ethernet. They are being utilized for automotive, and now some of the consortiums or some of the companies, they are thinking of silicon photonics for automotive. So why there is such kind of demand and necessity is because of the low power requirements, and then also the AI compute. So if you see in every technology, whether it is wireless technology or mobile communications or Wi-Fi, Bluetooth, or be it wired communications, everywhere there is a requirement of like, AI. Either you make a chip which is AI, which is an AI enabler, or which is or it is itself is an AI chip. And also, yeah, there is like both ways industry is working. Some of the companies, they are designing chips for enabling AI, and some of the companies are there who are developing EDA tools using AI. So they are AI-driven EDA tools, which makes your development faster. So in few years ago, when we used to develop chip, the development from the spec study to the tape out, or the product specifications to tape out, used to take 1 to 2 years. But now the companies, they target to develop and produce the chip within 1 year, and by the end of 1.5 year, they want the revenue to come in. So that is how the industry has revolutionized. And in that case, the growth for the talent requirements has also exploded. And you see, although the number of engineers coming out are more and more, but then because of the explosive growth of technology, like from TSMC, if you say the node or the foundry, for example, like TSMC from 90 nanometer or 180 nanometer, now they have scaled down to TSMC like 1.4 nanometer. And most of the bigger companies like AMD, or maybe Nvidia, or maybe Nokia, or somewhere, their requirement for talents has now scaled down up to like, on the advanced node, very advanced nodes of these foundries actually. So in that way, we as a industrial person, and also as an academician, we have to also, train our students to catch up these kind of technologies. But then the fundamentals remain the same. Only the thing is, we need to able to mentor the students how to connect those dots, how to scale their thinking in that directions, keeping the fundamentals intact. So now also there are with the advent of this AI and data center requirements, you see there are many companies who are not able to there are many startups, or there are many companies who are not able to design their own chips. Then what they do, the trend of custom silicon design has also come up. So when I talk to customers, I always get a lot of requirements, either for the manpower in specialized domains, or they are looking for trusted partners who wants their own proprietary, chip. That, for example, you might have heard about like, OpenAI or Anthropic. These are the companies, they don't have the chip design team, but they need their own chip with their own specifications to to produce their own chip. So what they do is they give contract to the bigger players who have already dominated the chip market for a long time. They are trusted. So you see, like for Amazon also, or for Meta, these companies like Broadcom, Marvell, and all, or for global Unichip corporations, or there is another company called Allchip. These are the companies who are doing custom silicon design for specific customers actually. So, and there are many different type of chips are now coming up actually related to AI. But one thing is, and then correspondingly, you can see the requirement of manpower is also growing. It's not like the requirement is not growing, but then this they require people with strong fundamentals. If they hire freshers, when then they want people who has done the real work actually. So we need, as a industrial partner or as a academic partner or academic trainer, we have to catch up with these kind of upcoming technologies, whether it is in the design side or whether it is on the foundry side, to train our students on these technologies actually. While resource is a constraint, so as an industry and academic partners, or we can partner with each other to train those students on the advanced problems that industry is facing, train them on the real problems which the industry is facing. So that is the necessity of the current time of the current industry trend actually. So yeah, so in that case, I would say there are opportunities, but then we have to motivate the students in the right directions. I'll just briefly touch upon like what we as at OG Silicon are also trying to do, and how we do it, and probably this is the way every company are doing it, especially the product design companies. So I came up with the idea of developing IoT based Ethernet chips, which can target. Our aspirational target is on the automotive side, but then the automotive's revenue cycle is very long, and as a startup bootstrapped, we cannot target this automotive as of now. But what we are designing is Ethernet IPs, which can be, you can say, Indian IP, Indian Ethernet IP, and we are trying to develop this Ethernet IP in India. And what we focus on is on the physical layer side of the Ethernet, low speed, which goes for industrial IoT, or you can say edge AI. And what we do is when we start, we write the product spec, we study the standard, which these standards come from IEEE. The consortium of industrial experts like Broadcom and Marvell and all, they used to they spent a considerable amount of time, and then they delivered this spec, and we use this spec, and based on this spec we try to develop the product. So when we study the spec, we try to first do the architecture and modeling. So architecture and modeling is one very essential part of any chip design. You do simulation modeling, you do your simulation model should mimic the actual chip, how the chip should work. And it also encompasses analog design. There is a lot of demand for the analog design engineers. They are very hard to find, and this is a very important. That's the analog design is a very, very important part of any chip you take, whether it is for the data centers or whether it is for the wireless communications or IoT. So analog is not going anywhere, and it has to be done correctly, and it has to be done in a right way. So analog engineers are very much in demand these days, and also the architecture engineer. So we need some system architects who understands the system as a product from the product point of view, from the cost point of view, and then the model the whole chip, whether it is on the analog side or whether it is on the digital side. And then we do there are tools in the EDA tools like high level synthesis or Xilinx, you can say, as a tool they have come up. So it's very easy to develop those RTL codes from C or MATLAB to RTL. It has been, I think, industry academicians have been using MATLAB for a long, long time. For so many years, they can use their MATLAB codes and then use MATLAB to HDL coder and all. There are tools where you can do the RTL design in a very efficient way and in a shortest possible time, and then go for verification and then the backend side. So now the developing the chips or developing the ICs, the design cycle has been cut short because the competition is growing and it is time to market actually. So that's so from the, if you say from the student's perspective, while every aspect of chip design is very important, there are opportunities in every design part or design cycle. And what we expect from the students is like their fundamentals should be correct, and it is better for them that they do their 6 months or 1 year of project very sincerely on advanced problem solving. Then it makes them, employable for a small startups or for big companies actually. Yeah, so for students like building a career in semiconductors, I should say the fundamentals is very important. Learn the modern languages and also build one real project, whether it is on FPGA or PCB or hardware design. Even PCB designers are very much in demand. And wherever your strengths are, just put more focus and master that part. So that will help us to help everyone to grow. And there is a lot of demand for good engineers, especially in the semiconductors. So this one aspect that I talked about in my presentation is on the design side, but yeah, that is equally important also on the process side, the foundry side. And I think the esteemed panelists in the previous panel discussion, they all rightly pointed out. I think it's a very short presentation from my side. Yeah, if you have any questions, let me know. Yeah.
Thank you, Chandan sir, for your valuable inputs and beautiful presentation, knowledgeable presentation for semiconductor. Now, I would like to extend my heart. Any question from the audience side? Any question? Any student want to ask any question? Okay. So I extend my heartfelt vote of thanks to our distinguished resource person, Mr. Chandan Jha sir, CTO of OG Silicon, for delivering such an insightful and inspiring session. Your deep understanding of the semiconductor industry, along with your clear explanation of emerging technologies such as 5G, 6G, IoT, automotive electronics, AI, health, hardware, and modern chip design, has greatly enriched our knowledge. We truly appreciate the time and effort you have taken to share your valuable industry experience with us. Thank you. Thank you very much, sir.
Thanks, Professor Chandashankar. Yeah, thank you.
So now all session of today has been completed, and I am thankful to all the resource person participants, and I'm now sharing my concluding summary about this summit. The one-day summit on Silicon India 2030 Vlsi and Chip Design Summit from Design to Fabrication, organized by the Department of Electronics and Communication Engineering, ESS, University of Noida, concluded successfully with enthusiastic participation from academicians, industry experts, researchers, faculty members, and students. The summit served as a significant platform for promoting knowledge sharing, fostering academia industry collaboration, and supporting India's vision of becoming a global semiconductor hub. The technical sessions covered a wide spectrum emerging semiconductor technologies. Professor Rajiv Ranjan sir from IIT Dhanbad introduced the concept of memory star technology, highlighting its evolution from theory to practical circuit and its application in neuromorphic computing, artificial intelligence, and energy efficient electronic systems. Dr. Kushwant Sara, University of Delhi, presented recently advancement in gallium nitride and gallium nitride based HEMT device, emphasizing their superior performance for high power and high frequency application. Dr. Ravindra Jha sir from IIT Guwahati discussed beyond silicon electronics, focusing on the potential of two-dimensional material for next generation semiconductor device and challenges associated with their large scale integration. In the afternoon session featured with Dr. Rajendra Pratap sir, Vice President and General Manager Varvi Semi Noida, who delivered an insightful lecture on advanced Vlsi design and emerging architecture. They highlighting AI chip and neuromorphic computing as the future of intelligent hardware system. This was followed by thought-provoking panel discussion on can India become a global semiconductor hub, where experts delivered on India's strength, challenges, policy initiative, skill development, and opportunity in semiconductor design and manufacturing. The summit concluded with an inspiring talk by Mr. Chandan Jha, founder of SEMI Taiwan, on chip design for 5G, 6G, IoT, and automatic system, emphasizing the transformative role in AI-driven computing, advanced chip architecture, and the skill required for future semiconductor challenges. Overall, the summit successfully achieved its objective of providing participants with comprehensive exposure to contemporary development in Vlsi design, semiconductor fabrication, AI hardware, wide bandgap semiconductor, beyond silicon technology, and future chip design trends. The expert lectures, technical discussions, and industry interaction enriched participants' understanding of cutting-edge technologies while inspiring innovation, research, and entrepreneurship in the semiconductor domain. The Department of Electronics and Communication Engineering extends its heartfelt gratitude to Honorable Vice Chancellor, University Administration, distinguished speaker. Gratitude to Honorable Vice Chancellor. Please mute the voice. Sorry for the interruption. The Department of Electronics and Communication Engineering extends its heartfelt gratitude to the Honorable Vice Chancellor, University Administration, distinguished speaker, organizing committee, faculty members, technical staff, student volunteers, and all participants for their invaluable support and contribution. The knowledge shared, collaboration established, and ideas exchanged during the summit will undoubtedly contribute to strengthening India's semiconductor ecosystem and advancing the vision of Silicon India 2013. Thank you. Thank you very much. Now, I would like to request Dr. Chaya Danela, madam. Please say the thanks remark for this summit.
Thank you, sir. Namaskar and good evening, everyone. With the divine blessings of His Holiness Jagadguru Shri Shri Ratri Deskandra Mahaswami Ji, respected Honorable Vice Chancellor Dr. H.R. Mahadev Swami Sir, respected Dr. B. Manoj Kumar Sir, Professor and Dean Academics, respected Registrar Madam Dr. T.J. Mamta Ma'am, CO Sir, AO Sir in absentia, esteemed Chairperson Summit Professor Dr. R.S. Jagdish, esteemed speakers Dr. Rajiv Ranjan from IIT Dhanbad, Dr. Kushwant Sehra, University of Delhi, Dr. Ravindra Jha IIT Guwahati, Dr. Rajendra Pratap, Viraswamy, Noida, Mr. Vijay Kumar, Director, Proexlera, Bangalore, Mr. Chandan Jha, Founder, Ogeswamy, Taiwan. Dear faculty members, researchers, industry experts, students, and participants from India and abroad. As we come to the close of this enriching summit, it's my privilege to speak before you all to place on records the contribution of every person towards the success of VLSI and chip design one-day online summit. The Department of Electronics and Communication Engineering organized today one-day online summit on Silicon India 2030 VLSI and chip design summit from design to fabrication today on 24th of July 2026. The summit witnessed an overwhelming response, bringing together academicians, industry experts, policymakers, researchers, professionals, and students from across the country and abroad. Through insightful expert talks and engaging panel discussion, the event served as an excellent platform for exchanging ideas on current trends and future vision of the VLSI technologies, VLSI design, chip fabrication, electronic design automation tools, and India's semiconductor mission. On behalf of the organizing committee, I, Dr. Chayadalilla, from the Department of Electronics and Communication Engineering, JSS University, Noida, extend our heartfelt gratitude to all our distinguished speakers, Dr. Rajiv Ranjan sir from IIT Dhanbad, Dr. Pushpan Sehra, University of Delhi, Dr. Ravin Jha from IIT Guwahati, Dr. Rajendra Pratap from Viraswamy, Noida, Mr. Vijay Kumar, Director, Proexlera, Bangalore, Mr. Chandan Jha, Founder, Ogeswamy, Taiwan, for sharing their valuable knowledge, expertise, and insights in the field of VLSI design. Sir, your thought-provoking sessions of all of the distinguished speakers have inspired us and broadened our understanding of emerging technologies. I express our sincere thanks to our esteemed panelists for their engaging discussions and for sharing diverse perspective on the future of research, innovation, and industry collaboration. Our heartfelt appreciation goes to all the dignitaries for gracing this occasion with their presence and encouragement. We, from the Department of Electronics and Communication Engineering, express our heartfelt gratitude to Dr. H.R. Madheswamy sir, Honorable Vice Chancellor, for his visionary guidance and encouragement in conceptualizing this summit. Dr. B. Manoj Kumar sir, Professor and Dean Academics, Professor Dr. Jagdish R.S., Dean SNW, Chairperson of One Day Online Summit. We sincerely thanks all the department heads, faculty members, and the organizing committee members for their constant guidance, encouragement, and unwavering support in making this summit a success. A special note of thanks goes to our technical team, volunteers whose dedication and hard work behind the scene ensured the smooth execution of every session. We are also grateful to all the participants for your enthusiastic involvement, insightful questions, and active participation. Your presence had made this summit truly meaningful. We hope the knowledge shared today will inspire new ideas, collaborations, and innovations in the field of VLSI domain that contribute to the advancement of technology and society. Thank you all for your active participation, and we look forward to meeting you all again in future academic and research initiatives. Once again, thanks to you all. Over to Dr. Achal.
Thank you, ma'am, for expressing our sincere gratitude to all the distinguished speakers, guests, faculty members, participants, organizing committee, volunteers, and everyone who contributed to the grand success of this summit. As we conclude today's program, I request everyone to kindly rise for national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब।
Now, I'm thankful to all the participants and the resource person for making this event a successful event. Thank you very much, everyone. Thank you. Now I can leave this. I permit this to leave this event now. Thank you very much.